There is a moment, and maybe you have had it without realizing what it was. You are somewhere far from the city. A camping trip, a long drive, a night. You ended up sleeping somewhere with no streetlights. You step outside, you look up, and everything you thought you knew about the night sky turns out to have been wrong, because the sky is not dark. It is full. It is overflowing, practically dripping with light, and running through the center of it is something that looks almost too strange to be real. A pale, luminous river, soft and wide-arching from one horizon all the way to the other. Not a cloud, not a smear on your glasses. Something ancient and enormous and alive with the light of 100 billion suns. That river is our home, and most of us have never truly seen it. Here is what nobody talks about. Enough more than 80% of people in North America cannot see the Milky Way from where they live. Not because it has gone anywhere, not because something happened to it, but because we built so many lights on so many streets and parking lots and office buildings left blazing through the night that we have effectively buried one of the greatest sights in the known universe under a permanent orange glow. An entire generation has grown up beneath a sky that has been quietly and without announcement switched off. Think about that for a moment. We are talking about something that has been visible to every human being who ever lived, every single one, going back 300,000 years until roughly the last century. Your great-great-grandmother could step off her porch on a clear night and watch the galaxy rotate overhead. Ancient farmers in the American Southwest built entire cities aligned to its position in the sky. Sailors crossed oceans by it. Poets wrote about it. Children were told it was the road the dead traveled to reach the other world. And now most of us have simply never seen it. Before we go any deeper into this story tonight, if you are enjoying what I bring to these long, quiet evenings, take one small moment to like this video, drop a comment, maybe subscribe, if this is the kind of thing that makes your nights a little better. It genuinely means everything to me when I know you are out there listening. And if you want to tell me where you are watching from right now, whether it is your bed, your couch, or maybe even a porch somewhere under an actual starry sky, I would love to know. Now dim the lights if you can. Get comfortable. Let tonight carry you somewhere far. Because what we are about to explore is not just a science lesson. It is something far more personal than that. The Milky Way is not out there. It is not a thing we visit or observe from a polite distance. We are inside it. Right now, as you listen to this, you are traveling through it, riding along with the sun at a speed of roughly 500,000 miles per hour, orbiting the center of a galaxy so large that even at that speed, one single lap takes 230 million years. The last time we were in this exact position in the galaxy, the age of the dinosaurs had not yet begun. There is something quietly disorienting about that if you sit with it long enough. We spend so much of our daily lives moving through very small distances. The commute, the grocery store, the walk from the parking lot to the front door. And then you step outside on the right night, in the right place, far enough from the nearest city, and the galaxy reminds you gently, without any drama, that the world you navigate every day is almost incomprehensibly tiny against the backdrop of where you actually live. The word galaxy comes from the ancient Greek word for milk, gala. The Greeks looked at that pale smear across the night sky and saw the spilled milk of a goddess. Hera, queen of the gods, was nursing the infant Heracles, and in her startled recoil, her milk sprayed across the heavens and became the stars. It is a beautiful story, and it tells you something important. Human beings have been trying to make sense of the Milky Way for as long as we have been capable of wondering about anything at all. Every culture that ever looked up at a clear night sky found a story for it. The Lakota people called it the Spirit Road, the path traveled by the dead on their way to the next world. The Khoisan people of southern Africa associated it with the embers of an ancient campfire, still glowing after the night had grown cold. In parts of Scandinavia, it was called the Winter Street, a road walked by migratory birds in autumn. In ancient China, it was a silver river in the sky, and along its banks lived two lovers, separated by its current, a story still celebrated every year in the Qi festival. None of them knew what it actually was. They only knew that it was there, constant and vast and unmistakably important, returning to the same part of the sky at the same time every year, like something that knew the schedule better than they did. The first person to look at the Milky Way and understand what he was actually seeing was Galileo Galilei in the year 1610. He turned his rudimentary telescope toward that pale glow, and what he found changed everything. It was not a cloud, not a river of divine milk, not the road of the dead. It was stars. Thousands upon thousands of individual stars, packed so densely together that from the naked eye they blurred into a single streak of light. In one small moment, with one small lens, the Milky Way went from a mystery of the heavens to a structure, something that had edges and form and could in principle be understood. But understanding it fully would take another 300 years and the combined effort of scientists across dozens of countries. And even now, in the 21st century, with space telescopes and radio arrays and supercomputers capable of modeling entire galaxies, there are things about the Milky Way that remain genuinely beautifully unexplained. That is what makes this story worth telling. Because the Milky Way is not simply a backdrop for human history, it is the condition that made human history possible. The precise location of our solar system within the galaxy, the particular age of our sun, the specific mix of elements that drifted through this corner of space 4.5 billion years ago, all of it conspired over an almost unimaginable stretch of time to produce a small, rocky planet with liquid water and an atmosphere orbiting at just the right distance from a middle-aged star in just the right region of a galaxy, not too violent, not too quiet, not too young, not too old. You are not an accident of the Earth. You are an outcome of the Milky Way. The physicist Carl Sagan once pointed out that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the very atoms we are made of, were forged inside the cores of stars that exploded long before our sun was born. We did not come from the Earth any more than a wave comes from the ocean floor. We came from out there, from the galaxy itself. And tonight, across the next several hours, we are going to spend some real time with this place we call home. Not the surface-level version, not the quick facts or the textbook summaries. We are going to go deep. We are going to talk about the invisible skeleton that holds the whole thing together, about the collision that is already in progress, about the black hole that sits at the center of everything, spinning and consuming and shaping the galaxy from the inside out. We are going to talk about stars being born in clouds of gas that glow pink and gold in the infrared, and about stars dying in explosions so powerful they briefly outshine an entire galaxy of 100 billion suns. We are going to talk about the question that keeps scientists awake at night, whether in all this vastness, in all these hundreds of billions of solar systems, we are somehow, improbably, alone. By the time this ends, the sky outside your window is going to look different to you. Not because anything about it will have changed, but because you will know in a way you maybe did not before what you are actually looking at. And right now, before any of that, before the black holes and the dark matter and the ancient stars older than the Earth itself, there is something even more fundamental we need to talk about. Something most people think they already understand, but do not. A shape and a size and a position that will quietly rearrange the way you picture this galaxy every time you close your eyes. What does the Milky Way actually look like? Not the symbol, not the photograph, not the diagram from the science textbook. The real thing. And why is answering that question so much stranger and so much more interesting than anyone warned us it would be? So let me ask you something. If someone walked up to you right now and said, "Quick, what does the Milky Way look like?" What would you picture? Most people, if they are being honest, would describe something like a fried egg seen from above. A flat disk with a bright bulge in the middle, 2 or 3 spiral arms curling outward like a pinwheel, everything neat and symmetrical and photogenic. The kind of image that appears on the cover of astronomy textbooks and NASA press releases, and the occasional motivational poster with a quote about being infinite. Here is the uncomfortable truth: that image is wrong. Not slightly off. Not a simplification for the sake of clarity, genuinely structurally wrong in ways that matter. And the reason we got it wrong for so long is one of the more quietly humbling stories in the history of science. We live inside the thing we are trying to describe. Think about what that means for a moment. Imagine being asked to draw an accurate map of the city you live in, but you are not allowed to leave it. You cannot climb above it. You have no satellite images, no aerial photographs, nothing but what you can observe from street level standing in one neighborhood looking outward. That is the situation astronomers have been in for centuries when it comes to the Milky Way. We are embedded inside a structure roughly 100,000 light-years across, somewhere about 26,000 light-years from the center, peering outward through clouds of gas and dust so thick that visible light cannot pass through them. It is a bit like trying to see across a room that is permanently full of fog. For most of human history, that fog won. We knew the galaxy was there. We could see its glow, but its true shape, the architecture underneath, remained stubbornly hidden. The first serious attempt to actually map the Milky Way came in the 1700s from a man named William Herschel, a German-born musician who had immigrated to England and taught himself astronomy with an obsessive dedication that by modern standards would probably raise some concerns. Herschel spent years building his own telescopes, larger than any that had existed before, and then systematically counted the stars in different directions across the sky. His logic was elegant. If you count more stars in one direction, the galaxy probably extends farther in that direction. By counting and counting and counting, he might triangulate the shape of the whole thing. His result was a flattened, irregular disk with the solar system sitting somewhere near the middle. It was a genuine breakthrough for its time. It was also, as it turned out, almost entirely wrong in its details because Herschel had no way of knowing that the dust clouds between stars were distorting his counts. He was essentially counting the fog and mistaking it for the room. It took another century and a half and an entirely different approach before the picture began to come clear. The real revolution came in the early 20th century when astronomers discovered a peculiar class of stars called Cepheid variables. These stars pulse, they brighten and dim in a regular rhythm, like a very slow heartbeat, and the critical discovery made by an astronomer named Henrietta Swan Leavitt, working at the Harvard Observatory in the early 1900s, was that the speed of that pulse is directly related to the star's true brightness. A Cepheid that pulses slowly is genuinely more luminous than one that pulses quickly. This meant that if you could measure how fast a Cepheid was pulsing, you could calculate how bright it actually was, Compare that to how bright it appeared, and from the difference, determine exactly how far away it was. Leavitt's discovery was, without exaggeration, one of the most important contributions to cosmology in the 20th century. She essentially handed astronomers a ruler that could reach across the galaxy. And yet for most of her career, she was not classified as an astronomer at all. She was a computer, a human calculator paid 25 cents an hour to analyze photographic plates. The discovery that would reshape humanity's understanding of the cosmos was made by a woman working in a role that barely acknowledged her as a scientist. She died in 1921 without receiving the recognition she deserved, and there is something quietly worth sitting with in that fact. Using her methods, an astronomer named Harlow Shapley determined in 1918 that the center of the Milky Way was not near our solar system at all. It was somewhere in the direction of the constellation Sagittarius, tens of thousands of light years away. The solar system, it turned out, was not at the center of the galaxy. We were out in the suburbs. Quiet neighborhood, decent schools, not much going on. That realization alone was a significant blow to human cosmic self-importance. First, Copernicus had moved the Earth away from the center of the solar system. Now, Shapley had moved the solar system away from the center of the galaxy. We were getting demoted at a fairly alarming rate. But here is what makes the true picture of the Milky Way genuinely stranger than the textbook version. The galaxy is not flat. For decades, the working model was a relatively thin disk, maybe 1,000 light-years thick at its outer edges, thicker toward the center, but broadly flat in the way a vinyl record is flat. Then, in the 1950s, radio astronomers began mapping the galaxy using radio waves which can pass through the dust clouds that block visible light. And what they found gradually was that the outer edges of the galactic disk do not lie flat at all. They warp. They bend upward on one side and downward on the other, like the brim of a hat that has been left out in the rain too long. This warping was puzzling enough on its own. Then, in 2019, a team of researchers using data from the optical gravitational lensing experiment released a new three-dimensional map of the Milky Way based on Cepheid variables, nearly 2,000 of them spread across the galaxy, and the picture that emerged was remarkable. The warp is not subtle. The outer disk curves dramatically, tilting up on one side by as much as several thousand light-years above the plane of the inner disk and drooping below on the other side. The Milky Way, our home, looks less like a pristine spiral and more like an enormous warped vinyl record left too close to a heater. The likely cause, and this is where it gets interesting, is gravitational interaction. The Milky Way is not alone in its neighborhood. It has companion galaxies, the most significant being the large and small Magellanic Clouds, two irregular satellite galaxies, visible to the naked eye from the southern hemisphere, orbiting our galaxy the way moons orbit a planet. The gravitational pull of the Magellanic Clouds appears to be tugging at the outer disk of the Milky Way over millions of years, slowly deforming its shape. Two galaxies dancing together in slow motion across billions of years, leaving a permanent wobble in the structure of our home. Now about those spiral arms, because this is another place where the popular image and the reality diverge in fascinating ways. The Milky Way is what astronomers classify as a barred spiral galaxy. The spiral part, you probably know, arms curving outward from the center like a pinwheel. But the barred part is less commonly discussed, and it changes the picture considerably. Instead of the arms emerging directly from a round central bulge, they emerge from the ends of an elongated bar of stars that cuts through the center of the galaxy. Think of the letter H, but with the crossbar much more prominent, and with the arms curling away from the ends of that bar. This central bar is enormous, estimated at somewhere between 27,000 and 37,000 light-years long, and it rotates as a solid structure, like a single rigid piece. Unlike the rest of the galaxy, which rotates differentially, meaning the inner regions orbit faster than the outer regions. Our solar system sits in a relatively minor feature called the Orion Arm, sometimes called the Orion Spur, which is not one of the four main spiral arms, but a smaller partial arm, branching off between two of them. We are, in galactic terms, living in a branch road rather than a main highway, and there is a genuine scientific debate about whether this particular location, this quiet mid-range, off the main arm position, is connected in any meaningful way to the conditions that allowed life to develop here. The galactic habitable zone is a concept that has gained real traction among astrobiologists over the past 2 decades. The idea is straightforward, even if the implications are not all parts of the galaxy are equally hospitable to the development of complex life. Too close to the center, and you are dealing with radiation levels that would be devastating to biological chemistry, along with the gravitational chaos of stars packed closely together, colliding and disrupting the stable planetary orbits that life seems to require. Too far out toward the edges, and the stars are metal poor. The early universe was almost entirely hydrogen and helium, and heavier elements like carbon and oxygen built up gradually over billions of years as successive generations of stars lived and fused and exploded. The outer galaxy simply has not had enough time and enough stellar generations to accumulate the elemental richness that biology requires. The habitable zone for life in the galaxy is, by current estimates, a ring-shaped region somewhere between roughly 13,000 and 33,000 light-years from the center. Our solar system, at about 26,000 light-years out, sits neatly within that range. We are, as it turns out, not just in any old part of the galaxy. We are in approximately the right part. Whether that is coincidence or something more meaningful is a question that planetary science and astrobiology are still actively wrestling with. But it is hard not to notice. There is one more element of the Milky Way's structure worth talking about here, and it is the one that tends to make people go quiet when they really absorb it. The galaxy is mostly empty. Not mostly empty the way a sparsely furnished apartment is mostly empty. Mostly empty the way the distance between atoms in your body is mostly empty, a scale of emptiness that does not really have a human equivalent. The nearest star to our Sun, Proxima Centauri, is approximately 4.2 light-years away. Light travels at roughly 186,000 miles per second. 1 light-year is the distance it covers in a full year of constant travel. 4.2 light-years means that even at that incomprehensible speed, it takes more than 4 years to get from our solar system to the nearest neighboring star system. If you scaled the Milky Way down so that the distance between our Sun and Proxima Centauri was the length of your arm, the full galaxy would be roughly the size of the United States. Most of that space between the stars is not entirely empty. It is filled with the interstellar medium, a thin soup of gas dust, cosmic rays, and magnetic fields that threads through the galaxy like a circulatory system. But the density of that medium is almost nothing. The best vacuums we can create in laboratories on Earth are millions of times denser than the average interstellar medium. Space is not dark and empty in the dramatic way science fiction likes to present it. It is dark and almost empty in a way that is actually harder to picture, because almost nothing is not nothing, and across the distances involved, even almost nothing adds up to something extraordinary. The interstellar medium is in fact where new stars are born. Regions where this thin gas and dust happen to be denser than usual giant molecular clouds, some of them hundreds of light years across, can under the right conditions begin to collapse under their own gravity. As they collapse, they heat up, and if the core becomes hot enough and dense enough, nuclear fusion ignites and a new star is born. The whole process from cold cloud to burning star takes somewhere between 1 million and 10 million years. By human standards, unimaginably slow. By galactic standards, practically overnight. There is something almost meditative about that timescale. The galaxy goes about its business on a clock that makes the entire span of human civilization, all 12,000 years of it, from the first cities to right now. You listening to this look like a blink. The Milky Way has been forming stars since long before our sun existed, and it will continue forming them long after the sun has gone cold. We arrived very recently at a party that started 13.5 billion years ago, and we are going to leave relatively soon on the cosmic scale of things. But we arrived, and we looked up, and we asked why. That curiosity, that very specific human impulse to look at something incomprehensibly large and want to understand it, rather than simply survive in its presence, might be the most surprising thing about our position in this galaxy. Not the habitable zone, not the distance from the center, not the particular composition of our solar system's raw materials. The fact that something in this small corner of a medium-sized barred spiral galaxy evolved the capacity to wonder about the galaxy itself. And now that you have a sense of where we actually are, the warped disk, the barred center, the quiet suburban spiral arm, the vast and tenuous space between the stars, there is a question that has been waiting in the background since we started. A question about something that was here, long before any of this structure existed. Something that humans have been trying to name and tell stories about since before we had telescopes, before we had writing, before we had cities. The oldest relationship between our species and the night sky. What did people actually see when they looked up, and what did they make of it? 40,000 years ago, give or take a few millennia, a human being stood in what is now the Australian outback and looked up at a sky so clear it would make you catch your breath. No cities, no roads, no electric light for 100,000 years in any direction. Just the night, enormous and close, pressing down like a living thing. And cutting across the middle of it, that river of pale fire we have been talking about. Wide enough to cast a faint shadow on a moonless night. Bright enough that you could, if you needed to, read by it. That person did not have a word for what they were seeing, but they had something arguably more powerful. They had time. Generations of time. Thousands of years of watching the same sky season after season, mapping its movements against the landscape, learning its rhythms, the way you learn the rhythms of a person you have lived beside your whole life. And what the Aboriginal Australians built from that accumulated watching is, by any reasonable measure, the oldest astronomical tradition in the history of our species. Here is what makes their relationship with the Milky Way genuinely unlike anything else in the ancient world. And I want you to stay with this because it is remarkable. Most ancient cultures looked at the night sky and drew meaning from the stars themselves. They connected bright points of light into constellations, told stories about them, navigated by them. The Aboriginal Australians did something that no other culture on Earth is known to have done. With the same sophistication, they mapped the dark spaces between the stars. They called these dark patches dark constellations, and they are exactly what they sound like. Where the Milky Way is thickest and brightest, dark clouds of cosmic dust create irregular shapes of relative darkness silhouetted against the glowing backdrop. To the trained eye, these dark patches form recognizable figures, an emu stretched out along the length of the galactic plane, with its head near the Southern Cross and its body extending towards Scorpius. A possum, a goanna, a caterpillar, a group of elders sitting together. The emu in the sky is perhaps the most studied of these. Its head, a dark cloud near the Southern Cross, called the Coalsack Nebula, rises above the horizon in the autumn months around April and May in the Southern Hemisphere. And here is the part that genuinely stopped researchers when they began to document it seriously. The appearance of the emu in a particular position in the sky corresponds almost exactly to the time of year when emus on the ground are nesting, when their eggs can be found and collected. The emu in the sky is a seasonal calendar encoded in the dark patches of the Milky Way, precise enough to guide food gathering across tens of thousands of square kilometers of landscape. This is not folklore dressed up as astronomy. This is functional, accurate, observationally derived knowledge, a system sophisticated enough that researchers at the Australian National University have described it as one of the most complex astronomical traditions ever documented. And it is at minimum tens of thousands of years old, possibly much older. Think about that the next time someone implies that modern science is the only serious way of knowing the sky. On the other side of the planet in Mesopotamia, the river valley between the Tigris and Euphrates in what is now Iraq, a different civilization was building a different kind of relationship with the night sky. The Babylonians, who flourished roughly from 1900 to 500 years before the Common Era, were meticulous observers. They kept detailed records of celestial phenomena on clay tablets, many of which have survived and been translated, and their observational database is so thorough that modern astronomers have actually used it to study historical patterns of lunar and planetary motion. The Babylonians had a name for the Milky Way too. They called it the River of the Ghost, or in some translations, the Great River that divides the sky. It appears in their astronomical texts as a fixed reference point, a structural feature of the heavens against which other phenomena were measured and recorded. What is interesting is that the Babylonians were not primarily interested in what the Milky Way was made of. That kind of question would not become central to astronomical thinking for another 2,000 years. They were interested in what it did, how it moved, what it predicted, because for the Babylonians, the sky was not separate from human life. It was interwoven with it. The positions of celestial objects at any given moment were believed to reflect or influence the conditions of the world, below the health of the king, the outcome of military campaigns, the flooding of the rivers. This was not superstition, in the dismissive sense we sometimes use that word. It was a coherent system of thought that took the sky seriously as a source of information, which is when you strip away the interpretive framework, not entirely unlike what modern astronomy does. The difference, of course, is in the method, and the moment that method changed is one of the more interesting intellectual ruptures in human history. It happened in ancient Greece, starting roughly in the 6th century before the Common Era, and the change was not primarily about technology. The Greeks did not have better telescopes than the Babylonians. They did not have any telescopes at all. What they had was a particular kind of philosophical stubbornness, an insistence that natural phenomena should be explained by other natural phenomena rather than by the will of gods or the influence of spirits. The sky, they argued, was not a message from divine beings. It was a physical system operating by consistent rules, and if it operated by consistent rules, those rules could in principle be understood. This sounds obvious to us now. At the time, it was a genuinely radical position. A philosopher named Democritus, working in the 5th century before the Common Era, proposed something remarkable about the Milky Way. Without any instrument more sophisticated than his own eyes and a disciplined mind, he argued that the luminous band crossing the sky was composed of an enormous number of distant stars, too faint and too numerous to distinguish individually, their light blending together into a continuous glow. He was correct. He arrived at essentially the same conclusion that Galileo would confirm with a telescope more than 2,000 years later, purely through reasoning from what he could observe with the naked eye. Democritus did not get much credit for this, partly because his contemporary Aristotle disagreed with him, and Aristotle had a habit of being loudly confidently wrong in ways that stuck around for centuries. Aristotle believed the Milky Way was an atmospheric phenomenon, a kind of exhalation from the Earth, ignited in the upper atmosphere by the heat of dense clusters of stars below. This view, wrong in essentially every detail, became the dominant explanation in the Western world for nearly 2,000 years, simply because Aristotle said it, and Aristotle's authority was difficult to argue with. There is a lesson somewhere in there about the difference between prestige and accuracy, but I will let you draw your own conclusions. In the Islamic world between roughly the 8th and 14th centuries of the Common Era, astronomers were doing work of extraordinary precision and sophistication, work that preserved, corrected, and substantially extended the Greek astronomical tradition at a time when much of that knowledge had been lost in Europe. An astronomer and polymath named Ibn Qayyim al-Jawziyya, writing in the 14th century, discussed the Milky Way in terms that pushed against the Aristotelian consensus. And an earlier scholar, Ibn Bajjah, known in Europe as Avimpas, writing in the 12th century in what is now Spain, explicitly argued that the Milky Way was composed of stars rather than atmospheric vapors, centuries before the idea gained widespread acceptance in European astronomy. These contributions are not minor footnotes. They are central chapters in the story of how humanity came to understand the galaxy, chapters that tend to get left out of the version of the story that begins with European scientific figures and stays there. In medieval Europe itself, the Milky Way acquired a different kind of significance. It became the Via Lactea, in Latin, the Milky Road, and in popular imagination, it merged with the pilgrimage routes that cut across the continent. The Great Pilgrimage Road to Santiago de Compostela in northern Spain, one of the most traveled routes in medieval Christendom, was sometimes called the Road of St. James, but it was also called the Milky Way because pilgrims used the galactic band overhead as a navigational guide across the dark landscape. The galaxy and the road were the same thing, one in the sky and one on the earth, both leading somewhere sacred. There is something poetic about that I find difficult to let go of. The idea that people traveling through the dark on foot for hundreds of miles would look up at the galaxy and see not a scientific mystery, but a path, a direction, an assurance that they were going the right way. Which brings us to the Inca, because the Inca cannot be left out of any honest account of human relationships with the Milky Way, and their approach to it combines something of the Aboriginal Australian tradition with something entirely their own. The Inca, whose empire stretched along the western coast of South America and reached its peak in the 15th century of the Common Era, called the Milky Way Mayu, the Celestial River. And like the Aboriginal Australians, they paid close attention to both the luminous band and the dark patches within it. They identified dark cloud constellations, a serpent, a toad, a llama with her cria, a fox, and integrated these into a sophisticated astronomical calendar that governed agricultural cycles, religious ceremonies, and civic life across an empire of roughly 12 million people. The Inca capital of Cusco was not laid out randomly. Archaeological and architectural analysis has shown that the city's streets, temples, and ceremonial lines, called sequoias, invisible lines radiating from the central temple outward across the landscape, were in part aligned to astronomical observations, including the position and movement of the Milky Way across the sky. The galaxy was not decoration, it was infrastructure. What strikes me most, thinking about all of these traditions together, the Aboriginal Australians, the Babylonians, the Greeks, the Islamic scholars, the medieval pilgrims, the Inca, is not how different their interpretations were. It is how consistent the underlying impulse was. Every culture that encountered the Milky Way felt compelled to do something with it. To name it, map it, integrate it into the structure of daily life, encode knowledge into it, find meaning in it. The specific meanings varied enormously, but the impulse to look up and take it seriously, that was universal. And then something changed. Not in the sky, the galaxy kept doing exactly what it had always done, rotating on its slow, majestic schedule, indifferent to human opinion. What changed was the instrument. In 1610, and yes, we are back to Galileo for a moment though, from a different angle than before, the telescope transformed the Milky Way from a subject of interpretation into a subject of investigation. But here is what does not get said often enough about that moment. When Galileo looked through his lens and resolved the glow into individual stars, he did not end the mystery. He deepened it. Because now there was a new question, one that the naked eye could never have generated. If those are all stars, then how many of them are there? How far away are they? How are they arranged? And are there others like this elsewhere in the universe? Each answer the telescope provided opened 3 more questions behind it. It has been doing that ever since. And the question that came next, the one that would consume astronomers for the following 3 centuries, was one of the most deceptively simple in the history of science. How big is it? Not the universe, just this one galaxy, just the Milky Way, just the thing we live inside. How large exactly is our home? The answer, when it finally came, was something nobody was entirely prepared for. And the way scientists arrived at it involved a series of mistakes, corrections, rivalries, and one extraordinary woman working in a building where she was not allowed to use the main entrance. Picture an architect standing before the most complex building ever constructed. Not complex in the way a skyscraper is complex, with its steel and glass and thousands of individual decisions made by individual people. Complex in the way a living organism is complex, where every part is in motion, every part is connected to every other part, and the whole thing is simultaneously falling apart and rebuilding itself continuously over timescales that make human civilization look like a coffee break. That is what we are dealing with when we try to understand the internal architecture of the Milky Way. Not a static structure, a dynamic one. A galaxy that has been assembling itself layer by layer for 13.5 billion years and is still not finished. Let us start with something that rarely gets mentioned in casual conversations about the galaxy, but that changes the picture considerably once you know about it. The Milky Way is not one thing. It is, in a meaningful sense, several things layered on top of each other, each with its own distinct history, its own population of stars, its own age and composition and origin story. Astronomers divide the galaxy into several broad structural components, and each one is worth understanding on its own terms. The first is what they call the thin disk, the flat star-rich pancake that contains most of the galaxy's visible matter, including our own solar system. This is the part of the Milky Way that produces the glowing band you see in the night sky. It is roughly 1,000 light-years thick in our neighborhood, though it gets thicker toward the center, and it is where nearly all of the galaxy's ongoing star formation happens. The thin disk is relatively young, as galactic structures go. Most of its stars formed within the last 8 billion years or so, though some are older, and it is chemically rich, meaning its stars contain substantial amounts of elements heavier than hydrogen and helium. In astronomical terminology, these heavier elements are called metals, which is a word that confuses people when they first encounter it, because astronomers classify carbon, oxygen, nitrogen, and essentially everything else on the periodic table beyond helium as a metal. A star described as metal-rich is not made of iron and copper. It simply contains a meaningful abundance of elements that were forged in earlier generations of stars and scattered into the interstellar medium through explosions and stellar winds before the next generation formed. The thin disk is, in a sense, the industrious part of the galaxy, the neighborhood where things are still being built. Surrounding it, and slightly older, is the thick disk, a puffier, more diffuse layer of stars extending perhaps 3,000 light-years above and below the galactic plane. The stars in the thick disk are generally older, somewhat less chemically enriched, and moving in orbits that are more tilted relative to the galactic plane than those of thin disk stars. These are the veterans. Stars that formed in the earlier, more turbulent phases of the galaxy's history when collisions and mergers were more frequent and the gas clouds from which stars condensed had not yet been seeded with the full abundance of heavy elements that later generations would inherit. The thick disk is thought to have formed, at least in part, from the debris of smaller galaxies that the Milky Way absorbed billions of years ago. When a satellite galaxy falls into a larger one, its stars do not simply vanish, they get incorporated into the larger structure, but their orbits retain something of their original character, slightly tilted, slightly eccentric, slightly different from the stars that formed in place. The thick disk may be in part a graveyard of absorbed galaxies, a layer of history written in stellar orbits. And then there is the halo. The halo is the part of the Milky Way that most people have never heard of, and it is in some ways the most astonishing component of all. Surrounding the disk, surrounding the entire visible structure of the galaxy, is an enormous, roughly spherical cloud of stars, gas, and dark matter that extends hundreds of thousands of light years in every direction. The stellar halo is sparse, almost eerily so. The stars within it are few and scattered compared to the disk, like isolated travelers moving through a vast, dark countryside. But what they lack in number, they more than compensate for in age. The halo stars are the oldest objects in the galaxy. Some of them are more than 13 billion years old, formed when the universe was less than 1 billion years old, before the disk had coalesced, before the spiral arms had taken shape, when the Milky Way was still a churning, irregular collection of gas clouds and proto-galactic fragments in the process of assembling themselves into something coherent. These stars carry in their chemical composition a record of the early universe. They contain almost none of the heavy elements that later stars would be born with, because in the universe's earliest billion years, almost none of those elements existed yet. To look at a halo star is to look at something that formed from the raw, nearly pristine material of the early cosmos. Mostly hydrogen, a little helium, and almost nothing else. There is something almost unbearably old about that. Scattered through the halo and clustering particularly around the outer reaches of the disk are structures called globular clusters. And if you have never spent time thinking about globular clusters, I would gently suggest that you are missing out on one of the more magnificent things in the galaxy. A globular cluster is a gravitationally bound sphere of stars, anywhere from tens of thousands to several million individual stars, packed into a region typically just a few dozen light-years across. At the center of a large globular cluster, the density of stars is so extraordinary that the night sky, as seen from a planet in that region, would be blazing with stars. Not the scattered points we see from Earth, but a continuous, overwhelming wash of starlight, with stars separated from each other by distances measured in fractions of a light year, rather than multiple light years. You would never experience true darkness. The Milky Way has approximately 150 known globular clusters. Each one is ancient. The oldest are roughly 13.2 billion years old, formed at the very edge of what was cosmologically possible given the age of the universe. They are, in a very real sense, fossils, relics of the conditions that existed in the earliest phase of the galaxy's formation, preserved in a kind of perpetual gravitational embrace, orbiting the galactic center on long looping paths that carry them far above and below the plane of the disk. Astronomers study globular clusters the way archaeologists study pottery shards, not primarily for what they are themselves, but for what they reveal about the conditions that produce them. The chemical compositions of globular cluster stars tell us about the elements available when the early galaxy was forming. Their ages constrain the timeline of galactic assembly. Their distribution in space helps us map the underlying mass distribution of the galaxy, including the dark matter that contributes far more to the total mass than any of the visible components. And here is where we arrive at something genuinely worth pausing over, because it connects directly to where we live. Our solar system sits in the thin disk. We are part of the galaxy's younger, more chemically enriched, actively star-forming layer. This is not coincidental, and it matters enormously. The heavy elements that make up the Earth, the silicates that form its rocky mantle, the iron and nickel of its core, the carbon and oxygen and nitrogen that are the molecular basis of all known life. None of these existed in the galaxy until enough previous generations of stars had lived fused elements in their cores and returned those elements to the interstellar medium through winds and explosions. Life, as we understand it, requires a galaxy that has already done considerable work. It requires a place that has been enriched by the deaths of many previous stars. The thin disk of the Milky Way, at the age when our solar system formed roughly 4.5 billion years ago, had been building up heavy elements for more than 8 billion years. It was, chemically speaking, ready. A planet like Earth could not have formed in the early galaxy, not in the first 1 billion or 2 billion years, because the raw materials simply were not there yet. Life is, among other things, the universe waiting long enough for the right conditions to exist. Now, within the thin disk itself, not all neighborhoods are equal. This is something that does not come up often enough, and I think it deserves a moment of genuine attention. The inner galaxy, the region within a few thousand light years of the central bulge, is in many ways a harsher environment than our own. Stars there are more densely packed, which means gravitational interactions between stellar systems are more frequent and more disruptive. The rate of supernova explosions, the violent deaths of massive stars, is higher in the inner galaxy, producing elevated levels of high-energy radiation that can be damaging to complex chemistry. The central region also hosts a supermassive black hole we will spend significant time on that shortly, whose periodic activity has, over geological timescales, flooded the inner galaxy with radiation powerful enough to affect atmospheric chemistry on nearby planets. The outer galaxy, conversely, is sparse and metal-poor. Stars there formed from gas that had been enriched by fewer previous stellar generations, meaning the planets they host, if they host planets at all, are less likely to have the elemental abundance needed to build rocky worlds with complex geology and chemistry. Between these two extremes, the dense energetic inner galaxy and the sparse metal-poor outer reaches, there is a ring-shaped region where the conditions thread the needle. Not too much radiation, not too little chemical richness. A place where rocky, geologically active planets can form, and where those planets can maintain stable orbits over billions of years without being too frequently disrupted by close stellar encounters. This is the region our solar system occupies. Not by design, obviously the universe does not plan things, but by the particular accident of where and when our solar system condensed from a collapsing cloud of gas and dust. There is a concept in biology called the Goldilocks principle, the idea that certain conditions need to be neither too extreme in one direction nor too extreme in the other, but just right for life to be possible. We usually apply it to a planet's distance from its star, but it applies at the galactic scale as well. The Milky Way has its own Goldilocks zone, and we are in it. Does that mean life exists only in this zone? Almost certainly not. The universe is too large and too varied for such a tidy rule to hold universally. But it does suggest that our location in the galaxy is not arbitrary. It is part of the chain of conditions that made this particular rock, orbiting this particular star, capable of supporting the kind of complexity we call biology, and eventually the kind of complexity we call consciousness, and eventually the kind of consciousness that lies in bed at night, listening to stories about the galaxy it lives in. Which brings me to something I want you to consider for a moment, because I think it reframes the whole picture. We tend to think of the Milky Way as our setting, the backdrop against which human life takes place, the scenery outside the window. But the galaxy is not the backdrop. We are not observers of it from a comfortable distance. We are inside it, made of it, shaped by it, dependent on its particular history and chemistry and position in space in ways so fundamental that they predate the Earth itself. The galaxy did not simply provide us with a home. It provided us with the atoms we are made of, the conditions under which those atoms could assemble into something living, and the billions of years of relative stability that allowed that something living to eventually become complicated enough to ask questions. The Milky Way is not where we live. In a very real sense, it is what we are. And at the center of all of it, at the geometric and gravitational heart of this vast, layered, 13-billion-year-old structure, something sits. Something that has been shaping the galaxy since before most of its stars were born. Something that for decades we could only infer from the behavior of everything around it, because we had no way to see it directly. Until on the 12th of May in 2022, we finally did. What we saw and what it means, and why the scientists in the room went very quiet when the image first resolved on their screens, that is where we are going next. On the 12th of May 2022, a room full of scientists went quiet. Not the polite quiet of people waiting for a speaker to begin. Something different, the kind of quiet that falls over a group of human beings when they are collectively absorbing something they have spent years, in some cases entire careers, working toward, and half wondering if they would ever actually see. The kind of quiet that feels, even to the people inside it, like a moment they will remember for the rest of their lives. On the screens in front of them was a photograph. Blurry by everyday standards, you would not frame it and hang it in your living room. An orange and reddish ring of glowing gas, asymmetrical and slightly lopsided, surrounding a dark central region that absorbed all light and gave nothing back. It looked, if you are being honest, a little like a cosmic donut that someone left too close to a heat lamp. But what it was the first direct image ever captured of the object at the center of our galaxy. The thing that has been sitting at the heart of the Milky Way for billions of years, shaping everything around it through the sheer, ungovernable fact of its gravity. The supermassive black hole known as Sagittarius A star, 4 million times the mass of our Sun, packed into a region roughly the size of the distance between the Earth and the Sun. Sitting 26,000 light-years away, which sounds very far until you remember that we are inside the same galaxy, and on a galactic scale, 26,000 light-years is practically next door. The image was produced by the Event Horizon Telescope, not a single instrument, but a global network of radio telescopes spread across multiple continents, from Hawaii to Chile to the South Pole, all synchronized so precisely that they effectively functioned as a single telescope the size of the entire Earth. The data collected by these observatories required so much storage capacity that it had to be physically shipped on hard drives to a central processing facility because no internet connection was fast enough to transfer it in a reasonable time frame. In the age of the cloud, they used a cargo plane. The processing of that data, turning raw radio wave measurements from 8 separate observatories into a coherent image, took years and involved algorithms so complex that one of the lead computational scientists, a young researcher named Katie Booman, became briefly famous when a photograph of her reaction to seeing the first successful reconstruction appeared online. She had developed key imaging algorithms as a graduate student and had spent years not knowing if the project would produce anything usable at all. Her expression in that photograph, a kind of startled, disbelieving joy, captured something that I think a lot of people recognized instinctively. The feeling of having worked very hard towards something you were not entirely sure was achievable and then achieving it. But before we talk about what that image revealed, I want to take you back to the beginning of this story. Because the discovery of Sagittarius A star did not happen on the 12th of May, 2022. It happened across half a century in increments through the work of dozens of scientists who each added one piece to a puzzle they could not yet see the full shape of. It begins, as so many things in modern astronomy do, with radio waves. In 1931, a young engineer at Bell Telephone Laboratories named Carl Jansky was tasked with a very practical problem, identifying the sources of static interference that disrupted transatlantic radio communications. He built a large rotating antenna on a farm in New Jersey and began systematically listening to the radio sky. Most of what he heard was what he expected: interference from thunderstorms, both nearby and distant. But there was one persistent hiss that he could not account for. It moved across his antenna in a regular pattern, rising and falling over a cycle of approximately 23 hours and 56 minutes. 23 hours and 56 minutes is the length of a sidereal day, the time it takes the Earth to rotate once relative to the distant stars rather than relative to the Sun. Jansky realized that the hiss was coming from a fixed direction in space, not from anything on or near the Earth. He traced it to the direction of the constellation Sagittarius. He had discovered, without entirely knowing what he was looking at, that the center of the Milky Way was emitting radio waves. Jansky published his finding in 1933. The astronomical community's response was, to put it diplomatically, underwhelming. Radio astronomy was not yet a recognized field. Most professional astronomers did not have the equipment or the conceptual framework to know what to do with his discovery. Jansky himself was reassigned to other projects by Bell Laboratories and never followed up the work. He died in 1950 at the age of 44, having inadvertently opened one of the most important windows in the history of astronomy and then been essentially walked away from by the people who should have known what he had found. It was an amateur astronomer, a radio engineer named Grote Reber, working alone in his backyard in Wheaton, Illinois, who first followed up Jansky's discovery seriously. Reber built a parabolic radio dish in his backyard in 1937 at his own expense and spent years systematically mapping the radio sky. He confirmed Jansky's galactic center source and published maps of radio emission across the Milky Way. His neighbors, according to accounts from the time, were largely baffled, which is honestly completely understandable. The formal identification of what we now call Sagittarius A star did not come until 1974, when astronomers Bruce Ballack and Robert Brown, using the National Radio Astronomy Observatory in West Virginia, detected a compact bright radio source at the precise center of the Milky Way. They named it Sagittarius A star, the star designation indicating that it was a particularly notable feature within the broader Sagittarius A radio complex. The name has stuck, though what it actually is turned out to be nothing like a conventional star. For the next 2 decades, the question of what exactly Sagittarius A star was generated genuine scientific debate. A massive black hole was the leading hypothesis, but proving it was another matter entirely. You cannot see a black hole directly by definition; it emits no light. What you can do is observe the behavior of everything around it and infer the presence of something massive enough to explain that behavior. This is detective work of a particular kind, where the suspect leaves only indirect evidence, and you have to reason backward from effects to causes. The case was built by 2 separate teams, working in parallel over roughly 2 decades, one led by Reinhard Genzel at the Max Planck Institute in Germany, and one led by Andrea Ghez at the University of California, Los Angeles. Both teams focused on the same target, the stars orbiting the galactic center at very close range. If something with enormous mass was sitting at the center of the Milky Way, the stars nearest to it should be moving in ways that betrayed that mass, orbiting faster than stars, further out tracing paths that curved more sharply, completing their orbits in shorter periods. What they found, using infrared telescopes that could peer through the dust clouds, obscuring the galactic center to visible light, was extraordinary. Stars near the center of the galaxy were moving at speeds that by any ordinary measure of celestial mechanics should be impossible. One star, designated S2, was found to be orbiting the central point in a period of roughly 16 years, completing a full elliptical orbit around something invisible in just 16 years, at a peak velocity of nearly 3% of the speed of light. Let me make that concrete for you. The Earth orbits the Sun, which has a mass of roughly 2 × 10⁻30 kilograms in exactly 1 year. For S2 to complete its orbit in 16 years, while following a trajectory that brings it within just a few light hours of the central point, the object at the center of that orbit must be several million times more massive than the Sun, compressed into a region smaller than our solar system. There is no known physical object that could produce those gravitational effects except a black hole, a very large one. Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics in 2020 for their work establishing the presence of Sagittarius A star. Ghez became only the 4th woman to receive the Nobel Prize in Physics, which is, and I say this not to derail the story, but because it is worth noting every time a statistic that reflects the history of who has been allowed to do this work as much as it reflects anything else. Now, what is a supermassive black hole, and why is one sitting at the center of our galaxy? A black hole at its simplest is a region of space where the concentration of mass has become so extreme that the escape velocity, the speed something would need to reach in order to fly away from it, exceeds the speed of light. Since nothing travels faster than light, nothing can escape once it crosses what is called the event horizon, the boundary beyond which escape becomes impossible. Not matter, not radiation, not information of any kind. Whatever crosses the event horizon stays there. The black hole grows. Supermassive black holes, objects ranging from millions to billions of times the mass of the Sun, are found at the centers of most large galaxies. This is not a coincidence. The relationship between a galaxy and its central black hole is one of the most active areas of research in modern astrophysics because the two appear to grow together, to influence each other, to be connected in ways that we are still working to fully understand. At 4 million solar masses, Sagittarius A star is actually relatively modest by the standards of galactic supermassive black holes. The black hole at the center of the galaxy Messier 87, the one that the Event Horizon Telescope imaged in 2019, 3 years before the Sagittarius A star image, is 6.5 billion solar masses. Against that, our galactic center's black hole is practically neighborly. But size is not the only interesting thing about Sagittarius A star. What makes it particularly intriguing is its behavior. Most supermassive black holes in other galaxies are what astronomers call active. They are continuously consuming large quantities of surrounding gas and dust, and in doing so, they release extraordinary amounts of energy across the electromagnetic spectrum. These active galactic nuclei can outshine their entire host galaxies by factors of hundreds. They are among the most luminous objects in the universe. They reshape the gas distribution of their host galaxies across enormous distances. Some of them drive jets of particles, moving at nearly the speed of light, across millions of light-years of intergalactic space. Sagittarius A star, by contrast, is almost entirely dormant. It is one of the quietest supermassive black holes known. Compared to the monsters blazing at the hearts of other galaxies, it is barely whispering. It accretes material at a rate so low that the energy output from the accretion process is roughly equivalent to what a small city uses in electricity in a year, almost nothing on the scales that galactic physics operates. Why is it so quiet? The short answer is that it has run out of convenient food. The immediate vicinity of Sagittarius A star is relatively sparse in the kind of cold, dense gas that black holes consume most efficiently. The gas that is present tends to be hot and turbulent, difficult to capture in large quantities. But this has not always been the case. There is compelling evidence that Sagittarius A star was dramatically more active in the past. Enormous bubble-shaped structures of energetic gas extending roughly 30,000 light-years above and below the galactic plane called Fermi bubbles, discovered in 2010 by the Fermi Gamma Ray Space Telescope, are thought to be the remnants of a massive outburst from the galactic center that occurred somewhere between 1 million and 4 million years ago. During that period, Sagittarius A star may have been producing energy at a rate millions of times greater than it does today, flooding the surrounding galaxy with radiation and driving powerful winds outward from the galactic center. 1 million years ago, our ancestors, early members of the genus Homo, walking the landscapes of Africa, would have been alive under a sky that contained near the southern horizon a faint but anomalous glow, a brightness at the center of the galaxy slightly greater than usual. They had no way of knowing what they were looking at. They could not have known that 26,000 light-years away, the black hole at the heart of their galaxy was going through a particularly energetic phase, but they were there, and it was happening, and the light from it, such as it was, crossed the distance between us and reached their eyes. There is something about that image, those early humans under that particular sky, that I find difficult to shake. We think of black holes, as remote and abstract, as textbook physics problems, as things that exist in a different register of reality from the one we occupy. But Sagittarius A star is not remote. It is the anchor of our galaxy. Every star in the Milky Way, including our Sun, orbits it. The structure of the entire galactic disk is shaped by its gravitational influence. The Fermi bubbles it exhaled millions of years ago still loom above and below the galactic plane, larger than most of the galaxy's visible disk. The black hole at the center of the Milky Way is not a distant curiosity. It is a foundational fact of our galactic home. And the fact that it is currently quiet, currently consuming almost nothing, currently generating almost no energy output, is from the perspective of life on Earth not an accident. It is part of why we are here. An active galactic nucleus produces radiation powerful enough to strip atmospheres from planets, disrupt the chemistry of interstellar gas clouds, and generally make the surrounding environment hostile to the development and persistence of complex life. The fact that Sagittarius A star went quiet before the Earth was even fully formed, before the first oceans condensed, before the first continents rose, before the first self-replicating molecules assembled themselves in some warm primordial pool, may have been one of the silent prerequisites for everything that followed. We owe something to the silence of that black hole. It is a strange kind of debt, but it is real. And yet, and this is where things get genuinely strange, the silence is not absolute. Sagittarius A star still flares. Not the massive sustained outbursts of its active past, but brief, irregular brightenings that can increase its energy output by factors of hundreds over periods of minutes to hours before fading back to its baseline quiet. These flares are observed regularly by telescopes monitoring the galactic center, and their cause is still debated. They may result from small clumps of gas falling into the black hole, or from magnetic reconnection events in the material orbiting it, or from the disruption of asteroids and smaller objects passing too close. In 2014, astronomers watched with anticipation as a dense cloud of gas, designated G2, made a close approach to Sagittarius A star, passing within a few hundred times the distance from the Earth to the Sun. Predictions varied widely about what would happen. Some expected a dramatic increase in activity as the black hole consumed the cloud. Others were more cautious. What actually happened was considerably more subdued than the dramatic scenarios suggested. Some increased activity, a few notable flares, but nothing close to the spectacular feeding event some had anticipated. The black hole, it turned out, was particular about what it ate. It consumed only part of the gas and let the rest continue on its way. Even in its quiet phases, even in its moments of relative restraint, Sagittarius A star reminds us that the center of our galaxy is not static. It is not a fixed point. It breathes in its way. It stirs. It flares. And somewhere at its heart, beyond the event horizon, where our physics breaks down and our equations run out of answers, something sits that we do not yet have the language to describe. That is perhaps the most honest thing I can say about black holes. Not that we understand them, but that we have gotten close enough to see their shadow, close enough to photograph the darkness at the center of our own galaxy, and the photograph raised as many questions as it answered, which is, if you think about it, exactly what a good mystery is supposed to do. The black hole is quiet now. The galaxy continues its slow rotation. The stars in their billions go about their business, burning, aging, sometimes exploding. And somewhere in all of that burning and exploding, something extraordinary is happening on a continuous basis. Something that the galaxy has been doing since long before our sun was born. Something that will continue long after it is gone. Stars are dying. And in dying, they are creating something new. What that process looks like from the inside, and why the death of a single massive star can for a few weeks outshine the entire galaxy it lived in, is a story that involves violence and beauty in almost equal measure. And it begins not with the end of a star's life, but with the moment it decides in the slow language of stellar physics that it cannot hold itself together anymore. Every single atom of iron in your blood was forged inside a dying star. Not metaphorically, not as a poetic flourish. Literally, physically, chemically, the iron circulating through your body right now, carrying oxygen from your lungs to your brain as you listen to this, was produced in the core of a massive star that lived and burned, and then collapsed and exploded billions of years before the Earth existed. The calcium in your bones, the oxygen you are breathing, the carbon that forms the backbone of every biological molecule in your body, all of it came from stars. All of it passed through the violent, spectacular process of stellar death before it could become anything else. This is one of those facts that sounds like something people say at planetariums to impress tourists, but when you actually sit with it, when you trace the chain of events from the birth of the universe to the atoms currently constituting your hand, it stops being impressive in a casual way and starts being something closer to overwhelming. Let us trace that chain. The universe began approximately 13.8 billion years ago in a state of extraordinary simplicity. In the first few minutes after the Big Bang, the only elements that formed in significant quantities were hydrogen, helium, and trace amounts of lithium. That is it. The entire periodic table, every element from beryllium to uranium, every atom that makes up every rock and ocean and living thing on Earth, none of it existed yet. The early universe was, chemically speaking, almost boring. A vast, hot, expanding cloud of the two simplest elements slowly cooling, eventually condensing into the first generation of stars. Those first stars, astronomers call them population 3 stars, though none have yet been directly observed, because they formed and died before any telescope existed to watch them, were almost certainly very different from the stars we see today. Formed from pure hydrogen and helium, with no heavier elements to complicate the physics, they were likely enormously massive by current standards. Some models suggest they could have been hundreds of times the mass of the Sun. They burned hot and fast, consuming their fuel in millions of years rather than billions, and when they died, when the fuel ran out and the core could no longer sustain the pressure against gravity, they did so with extraordinary violence. In those stellar cores, at temperatures of tens of millions of degrees and pressures that compress matter into states with no Earth-equivalent nuclear fusion, had been building heavier elements step by step. Hydrogen fused into helium, helium into carbon and oxygen, carbon and oxygen into neon, magnesium, silicon, sulfur. And at the very end of the sequence, in the cores of the most massive stars, silicon fused into iron. Iron is where stellar fusion stops, not because the physics changes in some arbitrary way, but because iron is the most stable nucleus. It sits at the bottom of the nuclear binding energy curve, meaning that fusing iron nuclei together actually requires energy input rather than releasing it. A star can generate energy by fusing lighter elements into heavier ones all the way up to iron. Beyond iron, the process runs the other way. So when an iron core builds up at the center of a massive star, the energy source that has been holding the star up against the inward pull of its own gravity simply stops working. What happens next takes approximately 1 second. The iron core collapses, not gradually, catastrophically. In roughly a quarter of a second, a core roughly the size of the Earth compresses down to a sphere perhaps 20 kilometers across, with a density so extreme that individual atomic nuclei are crushed together. The outer layers of the star, still falling inward, slam into this suddenly rigid core and rebound in a shockwave of almost incomprehensible energy. The result is a supernova, an explosion that for a period of days to weeks can outshine the entire galaxy the star lived in. The entire galaxy, hundreds of billions of stars, drowned out by the light of one dying sun. The Milky Way produces roughly 1 to 3 supernovae per century on average, though the last one observed directly from Earth occurred in 1604, which means we are statistically somewhat overdue. When the next nearby supernova occurs, it will be visible in broad daylight. Depending on its distance, it may cast shadows at night. But here is what makes supernovae more than just spectacular destruction. In the chaos of the explosion, in the extraordinary densities and temperatures generated in the collapsing core, and the outward racing shockwave elements heavier than iron are synthesized for the first time. Gold, silver, platinum, uranium. The entire range of heavy elements that cannot be produced by ordinary stellar fusion is generated in the extreme conditions of these stellar deaths, and then scattered outward into the galaxy at significant fractions of the speed of light. A single supernova can expel material equivalent to several times the mass of the Sun into the surrounding interstellar medium, seeding the next generation of star-forming gas clouds with a new complement of heavy elements. Every generation of stars that forms and dies enriches the galaxy a little further. The Milky Way today, after 13 billion years of this process, cycling through generation after generation of stars, contains elements in abundances that the early universe never had. We live in a chemically mature galaxy, one that has done the work over an almost incomprehensible span of time, of building up the raw materials that complex chemistry requires. You might wonder, how do we actually know any of this? The temperatures and pressures inside stellar cores are completely inaccessible to direct observation. We cannot put a probe in the center of a star. We cannot watch the iron core collapse in real time. How confident can we really be in these models? The answer is quite confident, and for a reason that is surprisingly direct. We observe the light spectra of supernovae, and the specific wavelengths present in that light tell us with chemical precision exactly which elements are being produced and ejected. When a supernova occurs, its light carries a fingerprint, a set of absorption and emission lines that identify the elements present as clearly as a laboratory analysis. Astronomers have observed thousands of supernovae in other galaxies and confirmed again and again the presence of the predicted elements in the predicted proportions. The models are not speculation. They are tested predictions that have matched observations consistently across decades of increasingly precise measurement. One particular supernova deserves special mention here because it transformed our understanding of what stellar death looks like in real time. On the 23rd of February 1987, a star in the Large Magellanic Cloud, one of the small satellite galaxies orbiting the Milky Way, exploded. Supernova 1987A, as it came to be known, was the closest supernova to Earth in nearly 400 years, close enough to be visible to the naked eye from the southern hemisphere. What made it uniquely valuable to science was not just its brightness. It was that hours before the light from the explosion reached Earth, something else arrived. First, a burst of subatomic particles called neutrinos. Neutrinos are produced in extraordinary quantities during the collapse of a stellar core, roughly 10 to the 58th of them in a typical core collapse event, which is a number so large it essentially loses meaning, and because they interact almost not at all with ordinary matter, they travel outward from the explosion site at nearly the speed of light, passing through the entire mass of the collapsing star as if it were not there. The light from the explosion, by contrast, has to fight its way through the overlying stellar material and takes hours to emerge. 3 separate neutrino detectors around the world in Japan, the United States, and the Soviet Union all registered a brief pulse of neutrino detections within a 12-second window on the morning of February 23, 1987. Just under 3 hours later, the light from the explosion arrived. That 12-second pulse of neutrinos, detected simultaneously on 3 continents by instruments that had been built for entirely different purposes, confirmed in a single, extraordinary observation that the core collapse model of supernova explosions was correct. It also told us something remarkable. A star 168,000 light-years away had exhaled a burst of particles that passed through the Earth as if the planet were made of nothing, and we caught them. We actually caught some of them. Supernova 1987. A continues to be observed today, nearly 4 decades after the initial explosion. The expanding shell of debris is still moving outward, lit from within by the decay of radioactive elements produced in the explosion. In recent years, images from the James Webb Space Telescope have revealed the structure of the debris in extraordinary detail, a complex asymmetrical ring of glowing gas still expanding at thousands of kilometers per second, carrying within it the heavy elements synthesized in the moments of the explosion. That material will eventually, over millions of years, mix with the surrounding interstellar medium and become part of the raw material for future stars and planets. This is the cycle. This is what the Milky Way has been doing for 13 billion years, and what it will continue doing for billions more. Stars form from collapsing clouds of gas. They burn for millions or billions of years, fusing lighter elements into heavier ones. They die quietly if they are small, or explosively if they are large, and in dying, they return their material to the galaxy enriched with elements that did not exist before. That material drifts and mixes and eventually collapses again into new stars, new planets, new possibilities. Our Sun is part of this cycle. It is, by current estimates, a 3rd-generation star, meaning the gas cloud from which it formed had already been enriched by at least 2 previous generations of stellar birth and death. The heavy elements in our solar system, including every atom in every living thing on Earth, have passed through the cores and the death throes of stars that no longer exist. We are, in the most literal sense, recycled stardust. Now, the Milky Way is currently forming stars at a rate of roughly 1 to 3 new stars per year. This might sound modest, and compared to some galaxies it is. Starburst galaxies triggered into furious star formation by collisions or other disturbances can form stars at rates hundreds of times higher. The Andromeda Galaxy, our nearest large galactic neighbor, is forming stars somewhat faster than the Milky Way at present. But the Milky Way's relatively sedate current star formation rate is again connected to the conditions that allowed life to develop here. A galaxy forming stars at a frantic rate is a galaxy experiencing frequent supernovae, elevated radiation environments, and gravitational chaos. The Milky Way's long, relatively quiet middle age, its current phase of steady but unspectacular star formation, has provided the stability that complex life seems to require. There are stellar nurseries in the Milky Way that you can actually see with the naked eye if you know where to look. The Orion Nebula, visible as the middle star in Orion's sword, or what appears to be a star, is in fact a vast cloud of gas and dust roughly 40 light-years across, currently collapsing in multiple places to form new stars. It sits about 1,300 light-years from Earth. The light you see when you look at it on a clear winter night left that nebula approximately 1,300 years ago, around the time the Tang dynasty was flourishing in China, and the Venerable Bede was writing the history of the English Church. Inside that glowing cloud right now, or rather 1,300 years ago, which is the same thing from our perspective, protostars are condensing from collapsing knots of gas. Some of them will stabilize into stars that burn for billions of years. Some will never quite manage to ignite and will become brown dwarfs, instead failed stars that glow faintly from residual heat but never achieve the core temperatures required for sustained fusion. A very few, if they manage to form planetary systems with the right conditions in the right locations, might eventually harbor something living. We have no way of knowing which ones. We can only watch the nebula glow and know that inside it, the process that made us is happening again. There is a kind of profound continuity in that, if you let yourself feel it fully. The galaxy does not know we are here. It does not care in any sense that the word care applies. It simply does what it has always done, collapsing gas into stars, burning those stars for as long as their fuel lasts, scattering their material back into space when they die, and starting the whole thing over again. We are not the point of this process. We are an outcome of it. An unlikely, improbable, deeply contingent outcome, but an outcome nonetheless. And threading through all of this, through every star that forms and every star that dies, through every supernova that enriches the interstellar medium, and every nebula that collapses into something new, is a substance that accounts for more of the galaxy's mass than all of these visible, luminous, spectacular processes combined. You cannot see it. You cannot touch it. Every detector we have ever built to find it directly has come back empty. And yet without it, the Milky Way would not hold together. The spiral arms would unwind. The galaxy would simply disperse into the void. It is the most abundant thing in our galactic home, and we have absolutely no idea what it is. Here is a number that should stop you cold. 85%. That is the proportion of all matter in the Milky Way and in the universe at large that we cannot see, cannot touch, cannot detect with any instrument yet built, and cannot explain with any theory yet confirmed. 85% of everything that has mass in our galaxy is invisible to us in every meaningful sense of the word. The stars you see when you look up at the night sky, the gas clouds glowing between them, the dust lanes threading through the spiral arms, the planets and moons and asteroids and comets, all of it, every single visible thing in the entire galaxy, accounts for only about 15% of the total mass. The rest is dark matter, and we have absolutely no idea what it is. I want to be precise about that phrase, no idea, because it is easy to say and easy to gloss over. Scientists are not being casually modest when they say this. The identity of dark matter is not a gap in our knowledge, the way, say, the exact mechanism of consciousness is a gap, something we suspect is there have strong intuitions about and are gradually closing in on. Dark matter is a gap of a different character entirely. We know it is there. We can measure its gravitational effects with great precision. We have known about it in one form or another for nearly a century, and despite billions of dollars spent on experiments specifically designed to detect it directly, despite some of the most sophisticated physics experiments ever constructed, despite decades of theoretical work by thousands of physicists, nothing. No confirmed detection. No definitive identification. It is the largest unsolved problem in physics, wearing the galaxy like a coat. The story of how we discovered it, or rather, how we discovered that something was missing, begins in the 1930s with a Swiss-American astronomer named Fritz Zwicky. Zwicky was by all accounts a difficult person. Brilliant, unconventional, and possessed of an ego calibrated to match. He once referred to colleagues he disagreed with as spherical bastards, explaining that they were bastards no matter which angle you looked at them from. This is, and I say this with genuine appreciation, a magnificent insult, and the fact that he coined it suggests he was at least as creative an insultsman as he was an astronomer. In 1933, Zwicky was studying the Coma Cluster, a massive collection of galaxies roughly 320 million light-years from Earth, and measuring the velocities of individual galaxies within it. By applying a principle called the virial theorem, which relates the average kinetic energy of a system to its potential energy, he calculated how fast the galaxies should be moving, given the amount of visible mass holding the cluster together. The answer he got did not match the observations at all. The galaxies were moving far too fast. The visible matter in the cluster, the stars and gas he could observe, was nowhere near sufficient to gravitationally hold the cluster together against the velocities he was measuring. By rights, the cluster should have flown apart long ago. Zwicky concluded that there must be substantial amounts of unseen mass, what he called dunkle materia, in German dark matter, providing the additional gravitational glue. His calculation suggested the cluster contained roughly 400 times more mass than what was visible. The astronomical community's response was once again largely indifferent. Zwicky's methods were disputed. His personality made collaboration difficult, and the idea of enormous quantities of invisible mass seemed more like a bookkeeping error than a genuine discovery. His finding was noted, filed away, and mostly forgotten for several decades. The idea resurfaced with much greater force in the 1970s through work that could not be so easily dismissed, partly because it was meticulous and reproducible, and partly because it came from a scientist whose patience and precision were essentially beyond criticism. Her name was Vera Rubin, and the story of what she found and how long it took the scientific community to fully accept what she was showing them is one of the more quietly remarkable narratives in 20th century science. Vera Rubin had been interested in galaxy rotation since the early part of her career, and she faced obstacles from the beginning that had nothing to do with her science. When she applied to graduate school at Princeton in the 1940s, she received a letter informing her that the astronomy program did not accept women. She went to Cornell instead, and then to Georgetown, where she completed her doctorate. For years, certain observatories were simply not available to her. There were no women's restrooms in the observer facilities, which was used as a justification for exclusion that tells you something precise and not flattering about the priorities of the institutions involved. Despite all of this, or perhaps partly because of it, she became one of the most careful observers in the field. In the late 1960s and through the 1970s, working with her colleague Kent Ford and using a sensitive spectrograph Ford had built, Rubin measured the rotation curves of spiral galaxies, meaning she tracked how fast stars at different distances from the galactic center were orbiting. The expected result was clear. If the mass of a galaxy is concentrated in its bright central regions where the stars are densest and the light is brightest, then stars in the outer regions should orbit more slowly, just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. Mercury zips around the Sun in 88 days. Neptune takes 165 years. The further from the center of mass, the slower the orbit. This is basic gravitational mechanics tested and confirmed across centuries of observation. It is Kepler's third law, and it works. Except that it did not work for galaxies. What Rubin and Ford found galaxy after galaxy after galaxy was that the rotation curves did not decline with distance from the center. They were flat. Stars in the outer regions of spiral galaxies were orbiting just as fast as stars, much closer to the center, in some cases even slightly faster. The galaxies were rotating as if the mass was spread through a much larger volume than the visible stars and gas could account for. As if each galaxy were embedded in a vast invisible sphere of additional mass, a halo of something that contributed gravitational pull without contributing any light. Rubin was cautious in her initial interpretations, careful not to overreach. But as galaxy after galaxy yielded the same flat rotation curve, the conclusion became impossible to avoid. Either our understanding of gravity was wrong at galactic scales, or there was matter we could not see. She publicly favored the dark matter interpretation, and she documented it with a thoroughness that made the data essentially bulletproof. By the early 1980s, the flat rotation curve evidence had accumulated to the point where the scientific community could no longer comfortably ignore it. Dark matter became, if not exactly accepted, at least seriously entertained. And then came the simulations. As computing power increased through the 80s and 90s, physicists began running numerical simulations of galaxy formation, attempting to model how galaxies assembled themselves from the primordial gas of the early universe under the influence of gravity over billions of years of cosmic time. The results were instructive and troubling in equal measure. Simulations run with only ordinary visible matter failed to produce galaxies that looked anything like the ones we actually observe. The structure was wrong, the timescales were wrong, the clustering patterns were wrong. When dark matter was added to the simulations, specifically when a component of smoothly distributed gravitationally interactive but otherwise non-interacting matter was included, the galaxies that emerged from the simulations began to match the observations with remarkable fidelity. The large-scale structure of the universe, the distribution of galaxy clusters, the cosmic web of filaments and voids, all of it matched with dark matter. None of it matched without it. This is in its way a more convincing argument for dark matter's existence than any direct detection could be, because it demonstrates that the same invisible ingredient that makes individual galaxies rotate correctly also makes the large-scale structure of the entire observable universe come out right. The hypothesis is not patching one problem. It is solving dozens of them simultaneously with a single addition to the model. So what is it? The leading candidates fall into a few broad categories, and none of them has been confirmed. The most extensively searched for are called weakly interacting massive particles, a class of hypothetical subatomic particles that would have the right properties to be dark matter. They would have mass, they would interact gravitationally, and they would not interact with light or with ordinary matter in any other way. They would pass through walls, through planets, through you right now without leaving any trace. Billions of them potentially streaming through your body every second, completely undetectable by any of your senses, completely undetectable so far by any detector we have built. Experiments designed to catch these particles have been running for decades in laboratories deep underground, buried beneath mountains and mine shafts to shield them from cosmic ray interference. The large underground Xenon experiment in the Black Hills of South Dakota. The Xenon experiment beneath the Gran Sasso Mountain in Italy. Pandax in China. Each one is essentially a tank of ultra-pure material liquid xenon, in most cases surrounded by sensitive detectors, waiting for the infinitesimal signal of a dark matter particle colliding with an atomic nucleus. Each one has come back empty. The non-detections have been valuable. They have ruled out large regions of parameter space, telling us what dark matter probably is not, but the positive detection has not come. Other candidates include Axion's extremely light hypothetical particles, originally proposed to solve a completely different problem in particle physics, which theorists noticed also have properties that would make them viable dark matter candidates. Axion detectors, which work on entirely different principles from the xenon experiments, are also running and also have yet to produce a confirmed signal. There are sterile neutrinos, hypothetical heavier cousins of the neutrinos that supernova 1987A sent streaming through our detectors, and primordial black holes and other more exotic proposals. And then there is the alternative that some physicists take seriously enough to have developed into a working research program that dark matter does not exist at all, and that our understanding of gravity is simply wrong at the scales where galaxies operate. This framework, called modified Newtonian dynamics, or by its acronym, proposes that the gravitational force law changes at very low accelerations, the kind present in the outer regions of galaxies, in a way that naturally produces flat rotation curves without requiring any invisible matter. The original proposal was made by Israeli physicist Mordechai Milgram in 1983, and it has had a persistent and vocal minority of supporters ever since. The honest position is that modified Newtonian dynamics explains some things very well, particularly the observed relationship between the luminosity of galaxies and their rotation velocities, but struggles with others, particularly the structure of galaxy clusters and the large-scale pattern of cosmic structure. Dark matter explains those things better. Neither framework explains everything perfectly. The field is genuinely unsettled in a way that makes it exciting to follow and uncomfortable to summarize. What I find most striking about the dark matter problem, and this is a personal observation rather than a scientific one, is what it says about the limits of human perception as a guide to reality. Everything we have ever directly experienced, everything our senses have ever told us about the world, pertains to ordinary matter. The stuff that makes up atoms, that makes up chemistry, that makes up biology. And it turns out that this familiar stuff, the only kind of matter we have ever touched or seen or tasted, is a minor component of the universe. We are made of the exception, not the rule. There is something deeply humbling about that, and also something oddly liberating. If 85% of the matter in the galaxy is invisible and unknown, then the universe is at least 85% more interesting than we thought. The mystery is not a failure. It is an invitation. Vera Rubin, who died in 2016 at the age of 88, spent the last decades of her career making the case that the flat rotation curves were real, the implications were real, and that science needed to take them seriously. She was nominated for the Nobel Prize in Physics multiple times without receiving it, an omission that remains one of the more widely cited examples of overlooked scientific achievement. The Royal Astronomical Society awarded her their gold medal in 1996, making her the first woman to receive it since Caroline Herschel in 1828. A gap of 168 years between women receiving the same award tells you again something precise and not flattering. The dark matter halo surrounding the Milky Way extends far beyond the visible disk. Current estimates put its radius at somewhere between 300,000 and 500,000 light-years, dwarfing the visible galaxy by a significant factor. If you could somehow make it visible, our galaxy would look nothing like the elegant spiral of the textbooks. It would look like a tiny luminous disk floating at the center of an enormous featureless sphere. The spiral arms, all that beauty, all that structure, would be a small, bright core surrounded by an invisible ocean. We live inside that ocean. We have always lived inside it, and we are only just beginning to understand what it is. But dark matter, extraordinary as it is only part of the invisible architecture of the universe. Because there is something else out there, something discovered, not by looking at how galaxies rotate, but by watching how the universe itself expands, that makes dark matter look almost comprehensible by comparison. Something that is not matter at all. Something that fills empty space and pushes the universe apart faster and faster toward a cold and lonely end that no one predicted and no one particularly wanted. It is the strangest discovery in the history of cosmology, and it changes what the future of the Milky Way and everything in it actually looks like. In 1929, an astronomer named Edwin Hubble published a finding that changed our understanding of the universe so fundamentally that it took the scientific community several years to fully absorb what he was saying. By measuring the distances to galaxies and comparing those distances to the velocities at which the galaxies were moving away from us, Hubble demonstrated something that almost no one had expected. The universe was expanding. Not exploding outward from a central point, the way a bomb explodes, but expanding in all directions, simultaneously, the way the surface of a balloon expands when you inflate it, every point, moving away from every other point, with no center, no edge, no preferred location. This was remarkable enough on its own, but the discovery that built on it, the one that came nearly 70 years later, and that nobody predicted, nobody wanted, and nobody has yet fully explained, was stranger still. In 1998, two independent teams of astronomers were using a particular class of supernovae as cosmic distance markers to measure how the expansion of the universe had changed over time. The expectation shared by virtually everyone working on the problem was that the expansion should be slowing down. Gravity pulls things together. The mutual gravitational attraction of all the matter in the universe should be acting as a brake on the expansion, decelerating it gradually over cosmic time. The only question was whether the universe contained enough matter to eventually halt the expansion and reverse it, collapsing back inward in what cosmologists called the Big Crunch, or whether it would expand forever but more and more slowly. What the teams found was neither. The expansion of the universe was not slowing down. It was speeding up. The distant supernovae were fainter than they should have been, meaning they were farther away than the models predicted, meaning the universe had expanded more than expected since the light left those stars. Something was pushing space apart, not pulling it together. Something that filled empty space itself, that increased as space increased, and that was currently winning its contest with gravity by a comfortable and growing margin. This something was named dark energy, and it accounts for approximately 68% of the total energy content of the universe. Dark matter, the invisible substance that stumped physicists for a century, accounts for about 27%. All ordinary matter, every atom of every star and planet and living thing that has ever existed, amounts to roughly 5%. We are 5% of the universe. The rest is dark matter and dark energy, and we understand neither. I mention dark energy here, not to dive deep into cosmology, that is a longer conversation for another night, but because it has a direct consequence for the future of the Milky Way that is worth understanding before we get to the main event of this chapter. Dark energy is the reason that most of the universe is already permanently beyond our reach. Galaxies far enough away from us are receding faster than light can travel between us, and them meaning that no signal we could ever send would reach them, and no light they emit will ever reach us. The observable universe is shrinking in the long run, not growing. The galaxies we can currently see are the galaxies we will ever be able to see, and over truly vast timescales, even those will fade from view. But there is one galaxy that is not moving away from us. One galaxy that dark energy's push is insufficient to counteract because it is close enough that gravity still wins. It is moving toward us, has been moving toward us for a very long time, and in approximately 4.5 billion years, it will arrive. The Andromeda Galaxy, also known by its catalogue designation Messier 31, is the largest member of what astronomers call the local group, the small cluster of galaxies to which the Milky Way also belongs. It sits approximately 2.5 million light-years away, which sounds comfortably remote, until you consider that on the scale of the observable universe, it is practically in our backyard. On a clear autumn night in the northern hemisphere, it is visible to the naked eye as a faint, elongated smudge near the constellation Andromeda, the most distant object a human being can see without any optical aid. That pale smudge is a galaxy containing roughly 1 trillion stars, about twice as many as the Milky Way, and it is currently approaching us at approximately 110 kilometers per second. The collision, and astronomers are confident enough in the trajectory to use that word, though with important caveats, is not a future possibility. It is a scheduled event. The Hubble Space Telescope has tracked the motion of Andromeda with sufficient precision to confirm not just that it is approaching, but that the trajectory is nearly direct. There is some uncertainty about the exact geometry. Andromeda may pass slightly to one side of a head-on collision, but the outcome is not in serious doubt. These two galaxies are going to interact dramatically and irreversibly, and the process has already begun. In fact, it began billions of years ago. The outer halos of the Milky Way and Andromeda are so vast that they are already overlapping. The fringes of our galaxy and the fringes of theirs are already interpenetrating, swapping material, already beginning the slow gravitational conversation that will eventually become a full merger. From the outside, from some hypothetical observer in a distant galaxy watching our local group, the collision is not an event. It is a process unfolding across billions of years in a kind of slow-motion cosmic choreography. Now, when most people hear the word collision applied to two galaxies, they picture something like what happens when two cars hit each other. Crumpling metal, shattering glass, the violent transfer of momentum between solid objects. And given that we are talking about two systems each, containing hundreds of billions of stars, the instinct to imagine something devastatingly violent is understandable. But this is where the reality of galactic scales produces a result that is genuinely counterintuitive. The collision of two galaxies is, in a very specific sense, almost entirely empty space, passing through almost entirely empty space. Remember what we established about the distances between stars. The nearest star to our Sun is approximately 4.2 light-years away. If you shrank the Sun to the size of a grapefruit and placed it on a table, the nearest neighboring star at the same scale would be roughly 17,000 kilometers away, on opposite sides of the Earth. The stars in a galaxy, for all their collective splendor, are extraordinarily isolated from one another. When two galaxies collide, the probability of any two individual stars actually hitting each other is, by reasonable calculation, essentially zero. The stars pass through each other's galaxy like two swarms of bees merging. The individual bees do not collide, but the swarms become thoroughly mixed. What does collide and collide energetically is the gas, the interstellar medium of both galaxies, those thin clouds of hydrogen and helium and dust that thread between the stars do interact directly. When two streams of gas meet at high velocity, they compress heat up and can trigger massive waves of new star formation. Galaxy mergers are often accompanied by extraordinary bursts of stellar birth, as the compressed gas collapses into stars at rates far exceeding anything that happens in an isolated, quietly evolving galaxy. For a period of perhaps a few 100 million years during the merger, the combined system could be forming stars at a rate many times its current pace, a brief, brilliant flourishing before the gas is consumed and the system settles into a new, quieter configuration. The shape of the resulting merged galaxy is something that computer simulations have modeled in considerable detail, and the results are striking. The two flat, elegant spiral disks, the Milky Way with its barred arms, and the Great Spiral of Andromeda, will not survive the merger intact. Spiral structure depends on relatively ordered circular orbits of stars within a disk. The gravitational disruption of a major merger scrambles those orbits, pulling stars out of their circular paths into long looping trajectories that cross the plane of the old disk at steep angles. Tidal forces between the two galaxies will draw out enormous streamers of stars, tidal tails. Astronomers call them, stretching hundreds of thousands of light years into the surrounding space. The resulting object, after the two systems have passed through each other, separated, and then been pulled back together by gravity over perhaps a billion years of subsequent interaction, will most likely be an elliptical galaxy, not a spiral. A large, roughly spherical or ellipsoidal cloud of stars with no disk, no spiral arms, no ongoing star formation to speak of, because by that point, most of the available gas will have been consumed in the starburst activity of the merger. It will be a different kind of object entirely. Some astronomers have given this hypothetical future galaxy a name, Milkomeda, or sometimes Milkdromeda. These are not official designations. They are the kind of name that scientists give things when they have spent enough time thinking about them to feel on friendly terms. At the center of Milkomeda, the two supermassive black holes, Sagittarius A star from our galaxy, and the comparable black hole at the center of Andromeda, will spiral toward each other, driven together by dynamical friction as they lose orbital energy to the surrounding stellar population. Eventually, over a timescale of perhaps millions of years after the galaxies themselves have merged, the two black holes will themselves merge, releasing a burst of gravitational waves, ripples in the fabric of space-time of extraordinary power. The resulting single black hole will be larger than either of its predecessors. The gravitational wave signal from this future merger, if humanity or any of its descendants are around to detect it, will be unlike anything our current detectors are designed to measure. It will be a low-frequency signal, spanning years in wavelength, rather than the fractions of a second that characterize the black hole mergers our detectors have caught so far. Detecting it would require space-based detector arrays of a scale that we have only recently begun to plan for instruments like the Laser Interferometer Space Antenna, currently in development, which will extend gravitational wave detection capabilities to the low-frequency range where supermassive black hole mergers leave their signatures. And what of the Earth? What of our Sun, our solar system, the small blue planet that has been the setting for everything that has ever mattered to us? The most likely answer, and this is one of those places where the science is genuinely reassuring if you were worried, is that nothing much happens to us directly. Our solar system sits far enough from the galactic center, and the stars are spaced so widely that the probability of our Sun experiencing a close encounter with another star during the merger is extremely small. The Sun will be gravitationally jostled. Its orbit around whatever passes for the galactic center in the merged system will change significantly over time. There is a small but non-zero probability, some estimates put it at around 12%, that during the close approach, our solar system could be flung to a radically different position, potentially out to the outer halo of the merged galaxy. But the odds favor something considerably less dramatic: the Sun continuing to exist, continuing to orbit in a galaxy that no longer looks like the one we inhabit today. There is a caveat worth mentioning, though. By the time the collision begins, in earnest, 4.5 billion years from now, the Sun will be approximately 4.5 billion years older than it is today. It will be in the later stages of its main sequence life, significantly brighter and larger than it is now, and the Earth, if it still exists, will almost certainly no longer be habitable. The gradual brightening of the Sun over geological time is expected to boil off the Earth's oceans within about 1 billion to 1.5 billion years long before the Andromeda collision becomes a serious local concern. The collision is not what ends life on Earth. The Sun's own aging does that quietly and inevitably on its own schedule. The galaxy merger is something that happens to whatever comes after us, or to nothing at all. I find there is something unexpectedly moving about that fact. The greatest event in the future history of our galaxy, the merger of 2 trillion star systems into one enormous elliptical cloud of aging suns, will unfold whether or not there is anyone left to watch it. The universe does not require an audience. It simply proceeds. But right now, in this precise moment of galactic time, at this particular address in the Orion arm of a barred spiral galaxy in the northern reaches of the local group, there are beings watching. Curious, carbon-based, improbably conscious beings who have spent the last few centuries building instruments sensitive enough to detect the approach of a galaxy 2.5 million light-years away, and who have done the calculations carefully enough to know what is coming and when. That is not nothing. In the long history of this galaxy, it might even be the most remarkable thing that has happened yet. Which leads us almost inevitably to the question that has been waiting in the wings since we began the question that the collision of 2 trillion star systems makes suddenly uncomfortably personal. In all of this, in all these hundreds of billions of solar systems, in this galaxy that has been forming stars for 13 billion years and has merged with dozens of smaller galaxies along the way, is there anyone else? Have other planets, in other solar systems, in other corners of the Milky Way, produced something that looks up and wonders? And if they have, why is the sky so quiet? It was a lunch conversation. That is how the story goes, anyway. The summer of 1950, Los Alamos National Laboratory, New Mexico. A group of physicists walking to the cafeteria, talking about a recent newspaper cartoon depicting flying saucers, which were very much in the cultural air at the time, and the conversation drifted the way conversations among physicists tend to drift toward the more fundamental question lurking beneath the joke. If the universe is as vast as we believe it to be, and if the conditions for life are not uniquely rare, then where is everybody? The man who asked that question out loud over lunch, with apparently genuine puzzlement rather than rhetorical flourish, was Enrico Fermi. One of the most formidable physicists of the 20th century, the architect of the first nuclear reactor, a man whose intuitions about physics were so reliable that his colleagues had a name for them. Fermi estimates calculations so well calibrated that they could reach approximately correct answers with minimal information. And in that cafeteria, Fermi looked at the numbers, the way he always looked at numbers directly, without sentimentality, and arrived at something that has been called a paradox ever since. The universe is approximately 13.8 billion years old. The Milky Way has been forming stars for most of that time. Many of those stars are older than our Sun by billions of years. If even a small fraction of them host planets, And if even a small fraction of those planets develop life, and if even a small fraction of that life eventually becomes technologically capable, then some of those civilizations would have had billions of years of head start on us. Billions of years in which to develop, to expand, to make themselves known across the galaxy. And yet silence, no confirmed signal, no artifact, no visitor, no unambiguous evidence that anyone else is out there. Where is everybody? That question has been seriously investigated for more than 60 years now, and the honest answer is that we do not know. But the ways in which we do not know have become considerably more interesting over time, and it is worth spending some time with them, because this is not an abstract philosophical puzzle. It is a question about the Milky Way, specifically about what has been happening in this particular galaxy for 13 billion years, and about what our own existence within it might or might not mean. Let us start with the scale of the problem, because I think it is easy to underestimate. The Milky Way contains somewhere between 200 billion and 400 billion stars. Current estimates from exoplanet surveys, particularly the data gathered by the Kepler Space Telescope over its 9 years of operation, which observed more than 150,000 stars simultaneously and detected thousands of planetary candidates, suggest that on average, every star in the galaxy hosts at least one planet. Many host several. The fraction of those planets that fall within the habitable zone of their star, the range of distances where liquid water could exist on the surface, is uncertain but not negligibly small. Conservative estimates put it at somewhere between 10 and 40% of Sun-like stars having at least one potentially habitable world. Do the arithmetic loosely, several tens of billions of potentially habitable planets in the Milky Way alone. And the galaxy is 13 billion years old. Life on Earth appeared within the first billion years of the planet's existence, suggesting that at least in our case, the emergence of life from chemistry is not an extraordinarily slow process. If that is anywhere close to typical, the galaxy has had ample time and ample real estate. And yet, in 1960, a young radio astronomer named Frank Drake sat down and tried to formalize Fermi's intuition into something quantitative. Working at the National Radio Astronomy Observatory in Green Bank, West Virginia, Drake wrote an equation now universally known by his name that attempted to estimate the number of technologically communicating civilizations in the galaxy at any given time. The Drake equation is not really a solution to the problem. It is more like a structured way of displaying our ignorance. It breaks the question of how many civilizations exist into a series of smaller questions: the rate of star formation, the fraction of stars with planets, the fraction of those planets that develop life, the fraction of life that becomes intelligent, the fraction of intelligent life that develops technology capable of interstellar communication, and crucially, the average lifespan of such a civilization, and then multiplies them together. The first few terms of the equation are now reasonably well constrained by observation. The rate of star formation in the Milky Way is known to within a factor of a few. The fraction of stars with planets has been pinned down considerably by the Kepler mission and its successors. The fraction of those planets in habitable zones is being actively refined. But the biological and social terms, the probability that life emerges on a habitable planet, the probability that it becomes intelligent, the probability that intelligence produces technology, the average duration before a technological civilization goes quiet, for whatever reason, these remain almost entirely unconstrained. We have exactly one data point for each of them ourselves, and a sample size of one is, statistically speaking, essentially useless for estimating probabilities. This is the heart of the Fermi paradox. Not that we have searched extensively and found nothing, we have barely searched at all relative to the scale of the galaxy, but that the numbers, even with conservative assumptions, suggest we should not be alone, and yet we have no confirmed evidence of company. The proposed resolutions to this paradox fall into a few broad families, and each one says something different about the nature of life, intelligence, and the galaxy we live in. The first family of explanations is the simplest: life is rare. Perhaps the emergence of life from chemistry is not straightforward at all. Perhaps our data point of 1 is deeply misleading, and the actual probability of abiogenesis on any given habitable planet is so small that Earth-like life events are separated by enormous distances in both space and time, making the galaxy effectively empty despite its size. Perhaps intelligence is rarer still. Complex multicellular life took nearly 4 billion years to appear on Earth after the first simple microbes, and the evolutionary steps that produced nervous systems, brains, and ultimately consciousness might be extraordinarily unlikely to repeat. The second family says, life may be common, but intelligence is a trap. There are several variants of this. One is the Great Filter, a concept developed by economist Robin Hanson in 1998, which proposes that somewhere along the path from simple chemistry to galaxy-spanning civilization, there is a step so difficult that almost no species successfully navigates it. The crucial and sobering question is whether that filter lies behind us or ahead of us. If the filter is something we have already passed, the emergence of the eukaryotic cell, perhaps, or the development of sexual reproduction, both of which appear to have happened only once in Earth's history, then we are among the vanishingly rare survivors, and our future is relatively open. If the filter lies ahead, if civilizations at our current stage of development almost invariably encounter something that ends them, whether self-inflicted or externally imposed, then the silence of the galaxy is a warning rather than a mystery. I try not to dwell on that second possibility too long before bed. A third family of explanations is more structurally interesting. The galaxy may be full of life, but the distances are simply too large for signals to bridge in any practical time frame. Light, and any signal we can send, travels at a fixed speed. The Milky Way is 100,000 light-years across. A radio signal sent from a civilization on the other side of the galaxy would take 100,000 years to reach us. If that civilization broadcast its signal 100,000 years ago, we might be receiving it right now, but they would have no way of knowing we exist, because our own radio signals, which began leaking into space in the early 20th century, have traveled only about 120 light-years so far. We are, in interstellar communication terms, an extraordinarily new voice, and an extraordinarily quiet corner of the galaxy would still look silent to us if the nearest civilization were more than a few hundred light-years away. There is also what might be called the zoo hypothesis, the idea that other civilizations are aware of us, but have chosen, for whatever reasons of ethics or protocol, not to make contact with a species at our current developmental stage. It is a discomforting thought, not because it implies hostility, but because it implies indifference, or a kind of patient watchfulness that we have no way of detecting or responding to. And then there are the signal searches themselves, which are worth discussing honestly. The search for extraterrestrial intelligence. The program of scanning the sky for signals of non-natural origin has been ongoing in various forms since Frank Drake pointed a radio telescope at 2 nearby stars in 1960 in what he called Project Ozma. In the 6 decades since, the search has expanded enormously in both scope and sensitivity. The most famous moment in the history of the search came on the 15th of August, 1977, at the Big Ear Radio Observatory at Ohio State University. A volunteer astronomer named Jerry Eman was reviewing computer printouts of recorded signals when he noticed something that made him circle the data in red pen and write in the margin a single word: "Wow." The signal, now universally known as the wow signal, lasted 72 seconds and matched in several specific and striking ways the predicted characteristics of a signal of extraterrestrial origin. It arrived from the right direction, at the right frequency, and with the right narrowness of bandwidth. It has never been detected again, despite numerous attempts to relocate it. Its origin has never been definitively explained, though several natural and artificial explanations have been proposed and contested. It remains nearly 5 decades later the most intriguing unresolved signal in the history of the search, not confirmed as extraterrestrial, but not explained away either. It sits in the record as a question mark. More recently, a fast radio burst detected in 2020 by the Canadian Hydrogen Intensity Mapping Experiment, a radio telescope in British Columbia, was traced to a source within the Milky Way for the first time. Fast radio bursts are brief, intensely bright flashes of radio energy first discovered in 2007, whose origin was debated for years. Most appear to come from other galaxies. The 2020 detection traced to a magnetar, a type of neutron star with an extraordinarily powerful magnetic field within our own galaxy, suggesting that at least some fast radio bursts have natural non-intelligent origins. But the broader population of fast radio bursts, particularly those arriving from other galaxies, remains an active area of investigation, and the full range of their possible origins is not yet settled. There is a more philosophical resolution to the Fermi paradox that I find myself returning to periodically, not because it is scientifically rigorous, but because it feels honest about the limits of the question. It goes something like this: we have been broadcasting radio signals for roughly 100 years. We have been seriously searching for signals for roughly 60 years. The Milky Way is 13 billion years old. The galaxy is 100,000 light-years across. The idea that the absence of confirmed contact within our first century of looking constitutes strong evidence of absence seems, when you actually sit with the timescales, a little like concluding that the ocean contains no fish because you have not caught one in your first afternoon of fishing. The galaxy may be full of quiet, patient, incomprehensibly ancient things that we have simply not yet learned to recognize. Or it may be empty in a way that makes our existence more improbable and more precious than we can comfortably hold in our minds. Both possibilities are real. The data at present cannot distinguish between them. What I am certain of is this: the question matters. Not because the answer changes what we do tomorrow, but because it changes what we understand about where we are. If we are alone in the galaxy, if this improbable chain of events that produced chemistry, biology, consciousness, and curiosity happened only once in 13 billion years and 100,000 light-years, then every thought we have, every story we tell, every moment of genuine human connection is the only such thing in the entire galaxy, the only light of its kind in 100 billion stars. And if we are not alone, if somewhere in the outer arms in a star system we have never catalogued, around a planet we have never seen, something else is also looking up and wondering, then we live in a galaxy rich beyond anything our instruments have yet confirmed. A galaxy where the emergence of mind is not a fluke, but a tendency, where consciousness is something the universe generates here and there, when the conditions are right, the way it generates stars. Either way, the Milky Way is not just a backdrop. It is the context within which the most important questions we can ask become possible. And understanding those questions, really understanding them, requires grappling with something we have been building toward throughout this entire journey. Something that took centuries to accomplish, that involved some of the most ingenious observational strategies in the history of science, and that produced, finally, a map. Not a complete map. The galaxy is too large, and we are too embedded within it for that. But a map detailed enough to reveal surprises that nobody anticipated. A map that showed us our galaxy is not the shape we thought it was, not the size we assumed, and not nearly as well understood as the textbooks implied. How we mapped the inside of something we are trapped inside, and what we found when we did, is a story of human ingenuity operating at its most patient and most persistent. And it starts, strangely enough, not with telescopes pointed outward at the stars, but with a satellite pointed carefully, precisely at the positions of 1 billion individual points of light, measuring each one with a patience that puts human ambition in a very particular perspective. Map-making has always been an act of extraordinary ambition, dressed up as practicality. The first maps were not philosophical projects. They were tools, ways of knowing where the water was, where the enemy territory began, where the mountain pass closed in winter. Practical, urgent, survival-oriented. But somewhere along the way, as the objects being mapped grew larger and more abstract, map-making became something else. It became a form of reckoning with scale, an attempt to hold something enormous inside something small, to compress a continent onto a piece of parchment, or an ocean into a grid of coordinates, or a galaxy into a data set that a human mind could navigate. Mapping the Milky Way is the most extreme version of this project that human beings have ever attempted. And the central difficulty, the one that makes it unlike any other map-making challenge in history, is the one we have already touched on, but have not yet fully examined. We are inside it. We cannot step outside and look at the whole structure the way you step back from a painting to see its composition. We are embedded in one small location, surrounded by dust clouds that block visible light across most of the galactic plane, trying to reconstruct the three-dimensional architecture of something 100,000 light-years across from a single, fixed vantage point. It is, to put it plainly, a genuinely absurd problem. And the fact that we have made as much progress as we have is a testament to the particular kind of stubbornness that seems to be one of science's most reliable qualities. The most fundamental tool in the astronomer's mapping kit is something called parallax, and it works on a principle so simple that you can demonstrate it right now without leaving your bed. Hold your finger up in front of your face, close one eye, and note where your finger appears to be against the background. Now close the other eye and open the first one. Your finger appears to jump. It has shifted its position against the background, even though it has not moved. This apparent shift, caused by the change in your viewing angle, is parallax. The closer your finger is to your face, the larger the apparent jump. The farther away, the smaller. Astronomers use the same principle, but instead of switching between two eyes, they use the Earth's orbit around the Sun as their baseline. By measuring the apparent position of a nearby star against the background of much more distant stars in January, and then measuring it again in July, when the Earth is on the opposite side of its orbit, about 300 million kilometers away from where it was in January, they can detect a tiny shift in the star's apparent position. From that shift, knowing the size of the Earth's orbit, they can calculate the star's distance with pure geometry. No assumptions about the star's brightness, no models of stellar physics, just triangulation. The problem is that parallax shifts are extraordinarily small. Even for the nearest stars, the angular shift amounts to less than 1 arc-second, less than 1/3600th of a degree. Measuring such tiny angles from the surface of the Earth through an atmosphere that blurs and shimmers proved enormously difficult. For the first 2 centuries after the telescope was invented, parallax measurements of stars remained beyond the reach of available instruments. The distances to even the nearest stars were unknown. The first successful stellar parallax measurement was made in 1838, independently and almost simultaneously by 3 astronomers working on different stars. Friedrich Bessel in Germany measured the distance to a faint star called 61 Cygni. Thomas Henderson in South Africa measured the distance to Alpha Centauri, the nearest star system to our Sun. Wilhelm Struve in Russia measured Vega. In each case, the measurement required years of painstaking observation, meticulous instrument calibration, and mathematics applied with a care that borders on the obsessive. What they found was sobering. The nearest stars were not merely distant in the way that mountains are distant, or even in the way that the moon is distant. They were separated from us by distances so large that the numbers expressed in kilometers become meaningless. Alpha Centauri, the closest stellar neighbor, turned out to be roughly 41 trillion kilometers away, a number so large that astronomers immediately abandoned kilometers as a unit and switched to the light year instead, which at least compresses the figure into something grammatically manageable, 4.2 light years. Close by galactic standards, utterly vertiginously remote by any human measure. If parallax works by using the Earth's orbit as a baseline, the obvious next step is to use a larger baseline to put a telescope in space, where it could make measurements free from atmospheric distortion, and where it could potentially use a much longer baseline by observing the same stars from multiple points in its orbit. This was the logic behind the Hipparcos satellite launched by the European Space Agency in 1989, which over its 4 years of operation measured the parallaxes of approximately 118,000 stars with a precision far beyond anything achievable from the ground. Hipparcos was transformative. It gave astronomers a reliable distance ladder extending to a few hundred light years from the Sun, a small bubble within the Milky Way, but one measured with genuine precision, rather than estimated from indirect methods. The catalog it produced became a foundational reference for virtually all of stellar astronomy in the 1990s and 2000s. But 118,000 stars in a galaxy of 200 to 400 billion is a tiny sample. It is less than a millionth of a percent. To map the galaxy properly, to understand its 3-dimensional structure, to trace its spiral arms, to measure the motions of stars in different regions, and reconstruct the gravitational field that produces those motions required something far more ambitious. That something was the Gaia spacecraft, also from the European Space Agency, launched in December of 2013, and still operating as of the time I am writing this. Gaia is without serious competition the most ambitious astrometric survey ever undertaken. Its mission to measure the positions, distances, and motions of approximately 1 billion stars, not 100,000, not 1 million, but 1 billion, with a precision that would have seemed fantastical to the astronomers of previous generations. To achieve this, Gaia rotates slowly in space, scanning the entire sky, repeatedly measuring the positions of stars to an angular precision of a few micro-arcseconds. A micro-arcsecond is 1/millionth of an arcsecond. To give you some sense of what that means, measuring a position to micro-arcsecond precision from the distance of the Earth-Sun system would be equivalent to measuring the width of a human hair from a distance of roughly 10,000 kilometers. From the ground to a satellite sitting over the opposite side of the world. By the time of its 3rd major data release in 2022, Gaia had produced distance and motion measurements for more than 1.5 billion stars. The dataset is so large that processing it required developing entirely new computational techniques, The full catalog, if printed in standard-sized text, would fill tens of millions of pages, and the map that has emerged from all of this data, the three-dimensional picture of the Milky Way that Gaia is progressively revealing, has been full of surprises. Not minor refinements to an already solid picture, but genuine revelations that required astronomers to revise their models in significant ways. One of the most striking findings concerns the structure of the galactic disk itself. We already know the disk is warped, that the outer regions bend away from the central plane in a pattern that has been attributed to the gravitational influence of the Magellanic Clouds. But Gaia's data has revealed that the warp is not simply a static deformation. It is precessing, rotating slowly, like the wobble of a spinning top that is running down, completing one full rotation of its orientation, approximately once every 600 to 700 million years. This means the warp is a dynamic feature, not a fixed scar. It is the galaxy responding in real time, or rather in geological time, to the gravitational forces acting on it. Even more striking is what Gaia has revealed about the history of collisions and mergers in the Milky Way's past. In 2018 analysis of the first major Gaia data release by a team led by astronomer Amina Helmi, produced one of the most significant discoveries in the history of galactic archaeology. By plotting the motions of nearby stars in three-dimensional velocity space, the team identified a distinct population of stars whose orbits were radically different from the majority. They were moving in highly elongated retrograde orbits, circling the galaxy in the opposite direction from most stars, with chemical compositions characteristic of a stellar population that formed in a different environment from the Milky Way's main disk. The interpretation was remarkable. These stars are the remains of a large galaxy that merged with the Milky Way between 8 and 10 billion years ago. A galaxy roughly the size of the small Magellanic Cloud, which fell into the Milky Way and was thoroughly absorbed, its stars scattered into the halo, and the thick disk, its identity as a separate object, completely erased, except in the orbital signatures that Gaia's measurements were sensitive enough to detect 10 billion years after the fact. The absorbed galaxy has been given a name, Gaia Enceladus, sometimes called the Gaia sausage, because of the distinctive elongated shape it makes when its stars are plotted in velocity space. And the Milky Way's encounter with it was not a gentle brushing past. It was a major event. The collision is thought to have significantly disturbed the early Milky Way, possibly contributing to the formation of the thick disk, heating the pre-existing stellar populations and triggering waves of new star formation. The Milky Way we live in today is partly the product of a traumatic ancient event that we had no knowledge of until a spacecraft measured the positions and motions of enough stars to see the echoes of the impact still ringing through the stellar velocities a billion years later. Since the identification of Gaia Enceladus, the field of galactic archaeology has expanded rapidly. Researchers have identified several other distinct stellar streams and substructures in the Gaia data populations of stars moving in coherent groups whose orbital properties suggest they are the debris of other ancient mergers or the remnants of dissolved globular clusters. The Milky Way, it turns out, has been a gravitational predator throughout its history, absorbing smaller galaxies and star clusters over billions of years, incorporating their populations into its own, while leaving subtle traces in the kinematics of its stars. The galaxy we see today is not a pristine original. It is an accumulation, a palimpsest written over and over by successive events, with Gaia finally providing us with the analytical tools to read the earlier layers. One of the more personally affecting aspects of the Gaia mission, and I recognize this is a strange thing to say about a satellite that measures star positions is what it represents in terms of the relationship between patience and understanding. Gaia measures each star it observes dozens to hundreds of times over its mission lifetime, with each individual measurement contributing a tiny increment to the final precision. The full scientific return of the mission will not be realized until years after the spacecraft stops operating, as researchers continue to mine the datasets for patterns. The people who proposed the mission in the 1980s, who worked through its design and justification over a decade of lobbying and planning, many of them knew they might not live to see the full results. This is a particular kind of commitment to knowledge, doing the work now so that people you will never meet can understand things you will never know. Science at its most generous works this way. Gaia has also been quietly revolutionizing our understanding of stellar physics along the way as a kind of bonus product of its precision measurements. By measuring the precise luminosities and colors of hundreds of millions of stars, it has produced the most detailed version ever created of what astronomers call the Hertzsprung-Russell diagram, the fundamental classification scheme for stars relating their temperature to their brightness. The sheer number of stars in the Gaia sample has revealed fine structure in this diagram that was previously blurred by sample size limitations. Subtleties in the distribution of stellar types, slight trends in stellar properties with galactic position, the signatures of stellar ages and chemical compositions, all of it visible now with a clarity that previous generations of astronomers could only have dreamed of. We are living, without quite realizing it, in a golden age of galactic cartography. The maps being drawn right now in the data releases and research papers and doctoral theses being written at universities and observatories around the world are the first genuinely three-dimensional, kinematically rich maps of our home galaxy. Not sketches, not approximations. Detailed, precise, data-dense maps that record not just where stars are, but where they have been and where they are going. And still, for all of this progress, the map is incomplete. Gaia sees optical light, which means dust lanes in the galactic plane remain largely opaque to it. The far side of the galaxy, separated from us by the dense obscuring central bulge, is still poorly mapped. The full extent of the outer disk and the nature of the structures beyond it remain active areas of investigation. The galaxy is large enough that even 1.5 billion stars represents a sample, not a census. But consider how far we have come. From William Herschel counting stars by eye through a homemade telescope in the 1780s, building a distorted map from incomplete data and arriving at roughly the right idea through essentially the wrong method, to a spacecraft measuring 1 billion stellar positions to micro-arc-second precision, revealing ancient mergers and dynamic warps and the chemical fingerprints of stars born in galaxies that no longer exist. 2.5 centuries. That is how long it took to go from the first systematic attempt to map the Milky Way to the data releases that are currently reshaping everything we thought we knew about it, which brings us finally to the oldest stars in that map. The ones that predate not just our solar system, but most of what we can see in the night sky. Stars so ancient that the light now leaving them began its journey toward us, when the universe was still very young, when the galaxy was still assembling itself, when the future was genuinely open in ways it no longer quite is. What those stars have witnessed and what their existence tells us about the deep history of the galaxy we live in is the story of where all of this began. Somewhere in the outer halo of the Milky Way, there is a star that has been shining since before the Earth's solar system existed. Before the sun ignited, before the molecular cloud that would eventually collapse into our solar system had even begun to contract. This star, designated in catalogues by a string of numbers rather than a name anyone would remember at a dinner party, is approximately 13.2 billion years old. The universe itself is only 13.8 billion years old. That gap of 600 million years is all that separates this star's birth from the birth of everything. When you look at that star through a telescope, and it is faint enough that you would need a serious instrument to see it at all, you are not just observing a distant object. You are looking at a witness, something that was present or nearly present at the beginning of almost everything we know. I find that thought genuinely difficult to hold, not because it is sad exactly, but because it collapses time in a way that nothing else quite does. History, as we usually think of it, is a human-scaled thing. A few thousand years of written records, a few tens of thousands of years of modern human behavior, a few 100,000 years of our species' biological existence. But this star was born when the universe was less than 600 million years old, when the first generation of stars was still living out their brief, furious lives, and it is still burning. Quietly, dimly, in the outer halo, circling the galactic center on a long, looping orbit that carries it far above and below the plane of the disk. It has been doing that for 13 billion years, going around and around, watching the galaxy assemble itself below. The Milky Way that this star was born into bore almost no resemblance to the one we inhabit today. In the very early universe, galaxies did not exist as coherent structures. They assembled gradually through the hierarchical merging of smaller clumps of gas and dark matter, a process that cosmologists call bottom-up structure formation. The Milky Way began as a collection of smaller proto-galactic fragments, each forming its own first generation of stars, gradually drawn together by gravity, merging and disrupting and reorganizing over hundreds of millions of years. The oldest stars in the halo are the survivors of this chaotic early period, or rather, the descendants of that era, since the very first generation of stars, those massive population 3 objects formed from pure hydrogen and helium, lived and died in millions of years rather than billions. What we see in the halo today are second and third generation stars born from gas that had been seeded with the first traces of heavy elements by those earliest stellar explosions. They are metal poor in the technical astronomical sense, containing only tiny fractions of the heavy elements that later generations of stars would take for granted, but they are not primordial. They are already, in some sense, the second chapter. A star called He 1406-0713. The kind of name that tells you immediately it was discovered by a survey, rather than by someone peering romantically through an eyepiece, holds the current record as one of the oldest confirmed stellar objects in the Milky Way, with an estimated age of approximately 13.2 billion years. It was identified through a painstaking process of spectroscopic analysis, measuring the precise wavelengths of light it emits and comparing the resulting chemical fingerprint against models of stellar evolution. The extreme poverty of its heavy element content, it contains perhaps 10,000 times less iron than our Sun relative to hydrogen, is the primary evidence of its age. Stars that formed early in the universe's history formed from gas that had barely been processed by previous generations. Their chemical compositions are time capsules, carrying in their spectra the fingerprint of an era we cannot otherwise observe directly. These ancient stars are studied with an intensity that might seem disproportionate to their individual obscurity. They are faint, chemically boring in some respects, and located in inconvenient parts of the sky. But they are the closest thing we have to a direct sample of the early universe. Each one is a piece of evidence about conditions that existed before the galaxy took its current form, before the disk had assembled, before the spiral arms had wound themselves into existence. They are, in the language of archaeology, primary sources. The field that studies them has a name that I think does justice to the ambition of the project stellar archaeology. Just as a terrestrial archaeologist might sift through layers of sediment to find artifacts from vanished civilizations, stellar archaeologists sift through the spectra of thousands of stars, looking for the chemical signatures of early cosmic conditions. The work is meticulous, slow, and deeply dependent on the kind of precision instruments that previous generations could not have imagined. And the picture it is building of what the early Milky Way looked like, how it assembled, what it consumed along the way, is one of the most ambitious reconstructions of a historical event ever attempted, because the galaxy has a history. A long, violent, complicated history, most of which left no written record and no surviving witnesses, only the orbital velocities and chemical compositions of the stars that came out the other side. We have already touched on Gaia Enceladus, the large galaxy whose merger with the Milky Way 8 to 10 billion years ago left detectable traces in the kinematics of nearby stars. But this was not the only significant merger the Milky Way has experienced. The picture that has emerged from the last decade of research is of a galaxy that built itself, at least in part, through a long series of acquisitions, smaller galaxies and globular clusters drawn in by gravity, stripped apart by tidal forces, and incorporated into the growing whole. The Sagittarius dwarf galaxy is perhaps the most spectacular current example of this process, still visible in progress. Discovered in 1994, remarkably recently given how significant it turned out to be, the Sagittarius dwarf is a small elliptical galaxy that is currently in the process of being torn apart and absorbed by the Milky Way. It is not a future event. It is happening now on a timescale of hundreds of millions of years. The Milky Way's tidal forces have stretched it into a vast stellar stream, the Sagittarius stream, that wraps around the galaxy in a great arc traceable across the sky in the positions and velocities of its component stars. Some researchers estimate that the Sagittarius dwarf has passed through the disk of the Milky Way multiple times over the past billion years, each pass stripping away more of its stars and disrupting its internal structure. There is an interesting twist to this story. Some scientists have proposed that the repeated passages of the Sagittarius dwarf through the galactic disk may have triggered waves of star formation in the disk each time it passed by compressing gas clouds that would not otherwise have collapsed. If this is correct, the Sagittarius dwarf is not just a victim of the Milky Way's gravitational appetite. It is inadvertently a contributor to the disk's star formation history. Perhaps in some indirect way, a contributor to the conditions that eventually allowed our solar system to form. One galaxy absorbing another, and in the process, seeding the conditions for something that neither of them could have anticipated. The Milky Way has consumed, by current estimates, somewhere between 50 and 100 smaller galaxies over its 13 billion year history. Each one has left some trace, a stellar stream here, a population of oddly moving stars. They're a gradient in chemical composition that does not quite fit the surrounding stellar neighborhood. Reading these traces is painstaking work, and the catalog of identified merger remnants grows with each new generation of survey data. Beyond the stellar streams and absorbed galaxies, the Milky Way's history is written in something even more subtle: the metallicity gradient of the disk. Stars closer to the galactic center are on average more metal-rich than stars in the outer disk, because the inner disk formed earlier and has had longer to be enriched by successive generations of stellar evolution. This gradient is not uniform. It has bumps and irregularities that reflect the turbulent history of the galaxy's assembly, but the overall trend is there, and it carries information about the sequence and rate at which different parts of the galaxy formed and evolved. Reading this gradient combined with the age distributions of stars in different galactic zones allows astronomers to reconstruct something that is in its own way extraordinary, a rough developmental timeline for the Milky Way. The halo formed first from the earliest protogalactic fragments. The thick disk assembled next, partly from material that formed in place and partly from the debris of early mergers. The thin disk, the part of the galaxy where we live, where most ongoing star formation happens, where most of the galaxy's current chemical complexity resides, formed last and has been the dominant site of galactic activity for the past 8 or 9 billion years. Our solar system, forming roughly 4.5 billion years ago, appeared well into the thin disk era, born into a galaxy that was already ancient by the time the sun's first light emerged from its birth cloud. We are, in geological terms, late arrivals. The galaxy had already done most of its growing, had already experienced its most dramatic mergers, had already settled into its current configuration long before the Earth existed. And yet, the Milky Way is not done. It continues to evolve, continues to form stars at its measured pace, continues to interact gravitationally with its satellites. The Magellanic Clouds, the large and small Magellanic Clouds, visible as bright, irregular patches from the southern hemisphere, are themselves being gradually drawn in. The Large Magellanic Cloud, at roughly 160,000 light-years away, is the Milky Way's largest current satellite, containing perhaps 10 billion stars. Models suggest it will eventually be absorbed by the Milky Way, probably in a few billion years, in an event that will be smaller than the Andromeda merger, but significant nonetheless, potentially triggering a burst of star formation and disturbing the outer disk in ways that current models are only beginning to map. The Milky Way has also been doing something that only became fully apparent. In recent years, it is surrounded by a reservoir of warm gas extending far beyond the visible disk and stellar halo. A vast, tenuous atmosphere of ionized gas called the circumgalactic medium, stretching hundreds of thousands of light-years in every direction. This reservoir is enormous. Some estimates suggest it contains as much mass as all the stars in the Milky Way combined. It is the galaxy's reservoir of future star-forming material gas that fell in from the cosmic web during the galaxy's formation and has been sitting there, gradually cooling, occasionally being replenished by stellar winds and supernova ejecta from the disk below. The circumgalactic medium is currently one of the most active research frontiers in galactic astronomy because understanding it is key to understanding why the Milky Way is forming stars at the rate it is, why it has not run out of star-forming gas already, and what its future evolutionary path will be. The answers are not yet fully clear. The instruments capable of studying this diffuse, faint, enormously extended structure in detail are only now becoming available, and the field is in that exciting early phase where every new observation seems to complicate the picture rather than simplify it, which is, as anyone who has followed science for a while will recognize, the sign that something genuinely interesting is being uncovered. There is a particular star I want to return to before we leave this part of the story, not one of the ancient halo stars, but a much more familiar one, the one that our own planet orbits. The Sun is in many ways a thoroughly unremarkable star. Middle-aged, middle-mass, middle luminosity, located in a middling neighborhood of a middling galaxy. But its very ordinariness is in some sense the point. The Sun is a representative sample of the kind of star that the Milky Way produces in large numbers, and what happens to it in the future is therefore a preview of what will eventually happen to most of the stars around us. The Sun is currently about halfway through its main sequence lifetime. It has been fusing hydrogen in its core for 4.5 billion years and has roughly 5 billion years of hydrogen burning remaining. After that, it will expand dramatically over the course of perhaps a billion years into a red giant, its outer layers swelling to perhaps 100 times its current radius, engulfing Mercury and Venus and possibly the Earth. The Sun's luminosity will increase dramatically during this phase, potentially vaporizing any remaining oceans and stripping away whatever atmosphere Earth might still have. After the red giant phase, the Sun will shed its outer layers in a slow, beautiful exhalation of gas and dust, a planetary nebula glowing with the ultraviolet radiation of the exposed hot core at its center. The expelled material will drift outward into the surrounding space, joining the interstellar medium, eventually becoming part of the raw material for future generations of stars and planets. And at the center of the expanding nebula, the compressed remnant of the Sun's core will cool and fade over billions of years, a white dwarf roughly the size of the Earth, slowly radiating away its stored heat into the surrounding darkness. That is the Sun's future. Quiet, inevitable, and in its own way, rather beautiful. Not an explosion, not a collapse, just a long, gradual letting go. The iron in your blood has already passed through processes like this, at least once forged in a stellar core, scattered by a stellar death, gathered again into a new generation of gas and dust. The Sun's eventual planetary nebula will send its atoms on the same journey. Everything cycles, everything returns. The galaxy is patient in ways that human language struggles to accommodate. And in that patience, in that 13 billion year accumulation of stars born and stars ended and stars recycled, there is something that I think is worth sitting with quietly for a moment before we arrive at the final chapter of this particular journey. The Milky Way has witnessed more than we can name. It has seen its own assembly from fragments. It has watched galaxies fall into it and dissolve. It has seen the first stars light up and burn out in millions of years. It has watched over geological spans of time as chemistry complexified and planets formed, and at least once, in at least one small corner of one outer spiral arm, something happened that has never been adequately explained and may never be fully understood. Something became alive, and then eventually became curious. And now at the end of this long journey through the galaxy's past and present and future, we arrive at the most personal question of all. Not about the physics of stars, or the mathematics of dark matter, or the timescales of galactic mergers, but about what all of this means. What it feels like to be a temporary carbon-based arrangement of atoms that the galaxy produced, looking back at the galaxy that produced it, and trying to comprehend the scale of what it is. That is where we are going now. The last chapter, and perhaps in some ways, the most important one. There is a question that children ask, and adults stop asking, not because they find the answer, but because they get busy. Why are we here? Not in the theological sense, though. That is a perfectly valid place to take it, but in the most literal, physical, cosmological sense. Why does something exist, rather than nothing? Why did the particular chain of events that produced this galaxy, this star, this planet, this moment, produce anything at all? Why, out of all the ways the universe could have arranged itself, did it arrange itself into something that can sit quietly in the dark and wonder about its own existence? I do not have an answer to that. Nobody does. But I have spent the last several hours walking through everything that had to happen, every specific, improbable, cumulative step for this moment to be possible at all. And I want to spend a little time with what that chain actually looks like when you lay it out. 13.8 billion years ago, the universe began in a state of almost perfect simplicity. Hot, dense, undifferentiated. Just energy and the most elementary particles expanding and cooling, the physical laws that govern everything we know, clicking into place in the first fractions of a second. Within the first 3 minutes, nuclear physics assembled hydrogen and helium from those elementary particles. The universe was now a gas, vast, formless, gradually cooling, with no stars, no galaxies, no structure of any kind beyond the faintest quantum fluctuations imprinted in those first moments, fluctuations so small that measuring them required one of the most sensitive instruments ever built. For roughly 380,000 years, the universe was opaque, so hot and dense that light could not travel freely through it, bouncing endlessly off the charged particles that filled the space. Then the temperature dropped below a critical threshold. Electrons combined with protons into neutral hydrogen atoms for the first time, and the universe became transparent. Light finally could travel. That first light released in a single cosmological moment, now stretched by billions of years of universal expansion into the microwave frequencies, is still detectable today. It is called the cosmic microwave background radiation, and it is the oldest light in the universe. We can measure it. We have mapped it. It is a photograph of the universe at the age of 380,000 years. In the slight density variations of that ancient light, the seeds of everything that followed were already present. Regions slightly denser than their surroundings would eventually, through the slow accumulation of gravitational attraction, pull in more and more gas. Over hundreds of millions of years, these overdense regions collapsed into the first stars, the first galaxies. The first galaxy clusters the cosmic web that large-scale surveys now map across billions of light-years. The Milky Way grew out of one of those density variations, a particular patch of space that happened to be slightly denser than its surroundings, that drew gas and dark matter toward it over billions of years, that hosted the early bursts of star formation, that built up the halo and the thick disk that absorbed smaller galaxies along the way, that settled gradually into the barred spiral configuration it currently holds. A particular history in a particular location, producing a particular set of conditions. And in one quiet region of that galaxy, an ordinary patch of the thin disk in a minor spiral arm, orbiting the galactic center at a pace that has kept it in the relatively calm middle latitudes of the galactic habitable zone. For billions of years, a molecular cloud collapsed 4.5 billion years ago into a new star and a surrounding disk of gas and rock and ice. Most of that disk was absorbed into the sun. The rest, the small fraction that did not fall inward, assembled through collision and accretion over tens of millions of years into the planets. One of those planets landed at exactly the right distance from the sun for liquid water to be stable on its surface. It had a large moon, the result of a collision with another protoplanet early in the solar system's history that stabilized its axial tilt and gave it regular seasons. It had a magnetic field that deflected the worst of the solar wind. It had plate tectonics that recycled carbon and maintained the long-term stability of its atmosphere. It was by any reasonable measure absurdly lucky. And this is the thought that makes you go quiet, perhaps not lucky at all. Perhaps in a galaxy of hundreds of billions of solar systems, some fraction of them simply produce these conditions as a matter of statistical inevitability. Perhaps the right conditions for life are rare, but not vanishingly rare. Perhaps there are thousands or millions of planets in the Milky Way where some version of this story played out. We do not know. But the uncertainty cuts both ways. The possibility that we are not alone is in some ways as humbling as the possibility that we are. What we know is that here, on this particular planet, in this particular solar system, something happened approximately 3.8 billion years ago that changed the nature of chemistry on Earth forever. A molecule, or a collection of molecules, or a reaction in some warm pool of mineral-rich water, or at a hydrothermal vent on the ocean floor. The exact setting is still debated, acquired the ability to make copies of itself. Not perfect copies. Copies with occasional errors, with variation. And because some variants were slightly better than others at making further copies, the variants that worked best left more descendants. That is natural selection stripped to its absolute minimum. And from that minimum, over 3.8 billion years, every living thing that has ever existed on Earth descended. The bacteria in your gut, the trees outside, the whales, the fungi in the soil, the flowers, every virus, every fern, every octopus, every songbird, all of them kin, distantly but genuinely connected through an unbroken chain of reproduction that runs back 3.75 billion years to whatever that first self-copying molecule was. The unity of life on Earth is not a metaphor. It is a measurable fact written in the genetic code that every living thing on this planet shares. And you sitting or lying, wherever you are right now listening to this, in whatever corner of the world you inhabit, are the current endpoint of that chain. Every ancestor you have ever had going back, not just through human history, but through the entire history of life, managed to survive long enough to reproduce. Every single one. An unbroken sequence of survival stretching back nearly 4 billion years. The odds against your specific existence calculated from the beginning are so astronomically small that the number has essentially no meaning. And yet here you are. Here is what I keep coming back to after all of this. After the black holes and the dark matter and the ancient stars and the colliding galaxies and the signals we have searched for and not yet found. The atoms in your body are on average about 13.5 billion years old. Most of the hydrogen in you, the hydrogen in your water, in the organic molecules that make up your cells, is nearly as old as the universe itself. It formed in this Big Bang, drifted through the early universe, eventually fell into the gas cloud that became the Milky Way, cycled through stars and gas clouds and stellar winds over billions of years, and eventually found its way into a molecular cloud that became the solar nebula, then the Earth, then the ocean, then biology, then you. The heavier atoms, the carbon, the oxygen, the nitrogen, the phosphorus in your bones and your neural tissue and your blood were forged in the cores of stars that died before the sun was born. They were scattered into space by stellar explosions, drifted through the interstellar medium, were swept up in the collapse of the solar nebula, became part of the Earth, became part of the ocean chemistry, became part of the first organisms, were cycled through billions of years of biological history before they became part of any animal, and eventually became part of a human being, and eventually became part of you. You are not made of the Milky Way, the way a house is made of bricks assembled from external materials by an external process. You are made of the Milky Way, the way a wave is made of the ocean. The distinction between you and the galaxy is at the level of atoms, a temporary arrangement of the same material. You are the galaxy organized differently. organized for a time into something that breathes and thinks and feels and listens to stories about where it came from. That is the thing that I think gets lost in the headlines about light years and black holes and the scale of the universe. The scale is not supposed to make you feel small, or rather, it can make you feel small. That is a valid response and an honest one. There is no use pretending the numbers are not vertiginous, but that smallness is not the whole story. The other half of the story is that the universe produced something capable of measuring its own scale, capable of detecting light that left a star 13 billion years ago, capable of photographing a black hole 26,000 light years away, capable of being moved by the idea that the iron in its blood was forged inside a dying star. The cosmos did not have to do that. It was under no obligation to produce anything remotely like consciousness. And yet here we are, these brief, improbable arrangements of ancient atoms asking questions about the thing that made us. If that is not extraordinary, I am not sure what extraordinary means. There is a scientist named Carl Sagan whose writing I return to periodically, not because he had all the answers, but because he had a particular quality of wonder that felt entirely genuine, unperformed, unforced, the wonder of someone who had looked at the data and been genuinely moved by it. He once wrote that we are a way for the cosmos to know itself. It is a sentence that sounds simple and lands differently the longer you sit with it. The Milky Way has been here for 13 billion years. For most of that time, for all but the most recent sliver of it, nothing in it knew it existed. The stars burned and exploded, and the gas drifted, and the black hole at the center quietly did what black holes do, and none of it was witnessed by anything capable of witnessing. And then, in one small corner, the galaxy produced something that could look back at it, that could measure it, that could tell stories about it to other beings across a network of light and electricity and shared curiosity. That is what we are doing right now. The galaxy is knowing itself through you sitting in the dark, listening. I want to take a moment before we part for the night to simply say thank you. Not in the way you might expect, not with the routine gratitude of someone going through a script. I mean it genuinely, the fact that you stayed with this through all the time scales and all the distances and all the physics and all the history, that you gave this night to thinking about where we actually are, that matters to me. These stories only become real in the listening. You completed something tonight just by being here. If any of this has moved you, if you found yourself pausing on a particular idea or wanting to tell someone about what you heard, I would love for you to share it. These are the kinds of conversations I think we need more of. Slow ones, quiet ones, the kind you have in the dark, with no agenda, except understanding something a little more clearly than you did before. And if there is a story you want me to tell next, a civilization that vanished, a discovery that changed everything, a mystery that science has not yet solved, leave it in the comments. I read them. I take them seriously. Some of the best journeys I have taken started with a suggestion from someone who was just like you, listening late at night with the lights off. The next story is already being built, and I think if you like this one, you are going to find it worth the wait. For now though, rest. Let everything we have talked about settle into whatever quiet corner of your mind keeps things that matter. The galaxy will still be there when you open your eyes. The stars will have moved a little, barely perceptibly, on a human timescale, and the galactic center will be a little further along in its rotation, and somewhere in the outer halo, an ancient star will still be burning, circling in the dark as it has been doing for 13 billion years. And you will wake up as what you have always been, and what we have spent this whole night exploring. A temporary arrangement of very old atoms in a galaxy that learned through you to wonder about itself. Sleep well.